Across the world, towns and cities are often separated by vast wildernesses. Inhospitable landscapes, punishing terrain, and extreme weather can make crossing these divides seem impossible. But trains stop at nothing, tackling previously uncharted territory with some of the most adventurous railways on the planet. Overcoming the world's wildernesses poses uniquely difficult challenges for even the most pioneering of railway engineers.
Wilderness like this would stop any train in its tracks. This is an incredible feat of engineering.
So this is the start of the real climb. We're onto one of those tight curves. This is real mountain railroading.
It's bleak, it's isolated, it is utterly treeless. How can you build a railway here? What would you build it out of?
And it's one such seemingly impossible challenge that faced engineers in North America in the late 1800s. When you're building a railway across an entire continent, it's inevitable that you'll encounter wilderness along the way. But when the terrain ahead goes underwater, then you could be left with a sinking feeling. Promontory Summit, Utah is in the heart of America's Mountain West. It's an empty desert landscape with few signs of civilization, as engineer Dan Dickrell is finding out.
Gosh, you know, there's really nothing out here. If you've ever driven across the western United States, there's these vast tracts of nothingness. This is the last place I would expect anything to happen, let alone an important piece of American history. It's fair to say it's pretty barren out here.
However, this unlikely spot did play host to perhaps the most significant moment in the annals of the North American Railroad. Since the inception of railways, engineers had dreamt of building a line that would connect America's East and West. And in 1869, that was about to become a reality.
Oh, this is a really cool moment. So I'm riding on the Jupiter, which is an exact replica of the steam locomotive that would have been here when the two railroads met from east to west. For the first time, you could ride from one end of the continent to the other. I can't describe to you how cool this is because this is a beautiful reproduction. It's in pristine condition. It weighs 60 tons, about 10 African elephants. It burns all of its fuel in about 30 miles. Which is not a lot. It goes about 25 miles an hour. It's 2,000 gallons of water to make the steam. It's a huge but beautiful machine. Well, here it is. This is the Golden Spike. This is the location where the two lines met and were united.
But this tricky route through Promontory Summit was in fact always Plan B. Because traversing the steep grades and tight curves of this mountainous terrain added 68 kilometers onto an already epic journey. Plan A, however, was seemingly impossible.
This is the Great Salt Lake. It is a mind-blowing sight when you're here. It's so massive, it's so vast. You can't see the other side. The sky and the water blends together. It's incredibly bright out here.
This phenomenal watery wilderness would pose engineers with a colossal challenge.
Standing in this spot, it's easy to imagine what those engineers felt so long ago trying to figure out how they're going to cross this vast body of water. It seems almost impossible.
Until 1902, when taking on the 4,400 square kilometers of hostile landscape became a necessity, as the route through the mountains had become an arduous bottleneck.
It's not even a bad day, and it's really choppy out here. The water, it's 6 times saltier than ocean water. Makes for a really dense and powerful wave. As an engineer, when you want to build something, you have to take into consideration the environment. And this is probably one of the most aggressive environments that you could build anything, right? Extremely salty water, high humidity, high heat in the desert. It's not a very hospitable place for something that's supposed to last for a long time. So I wouldn't want to build anything out here at all.
The monumental solution engineers came up with was the Lucin Cutoff. For a year and a half, 3,000 men grafted to build 2 earth and rock-filled embankments, bridged in the middle by an immense wooden trestle.
This is the point where the old original trestle would have started extending out into the lake. It was 12 miles of timber. 2 square miles of forest were used to make this immense wooden structure.
In 1904, a train passed over the lake for the first time, cutting the journey through Utah from 10 hours to a mere 2 hours. But by the 1950s, conditions had taken their toll on the trestle bridge.
The pilings themselves weren't driven that far into the lake bed, and the lake bed in this particular lake is very soft. So the weight of the trestle itself, as well as trains, would cause subsidence. The trestle would sink. The aggressive nature of salt infiltrating the wood would cause it to split and deteriorate. Ultimately, it was decided that the trestle was to be torn down and replaced with something stronger. It's too bad. It would have been a magnificent sight today. But ultimately, this lake is just too much to handle for a wooden structure.
Faced with such extreme conditions, engineers had to find a more robust solution. In 1956, work began to create one epic causeway that would carry the railway on a raised stone embankment across the entire span of the lake.
This is the causeway. It stretches almost as far as the eye can see. Tons and tons of fill rock are dumped into the lake, something to build a track upon.
75,000 tons of rock was transported daily on 6 of the largest bottom dump barges ever constructed.
Seeing workers on top of the causeway gives a sense of the epic scale of this work, the size of the boulders, the elevation above the lake. It's massive. It's a massive structure.
But once again, Mother Nature showed her hand.
Now these rocks and boulders that fill the causeway look large, but the forces that this lake can bring to bear are even larger. But it's a testament to how heavy this causeway is and how soft and squishy the lake bed is. It's always sinking, always subsiding. And so it's a continual battle to replenish this structure and a constant fight against the environment. That engineers, the rail line are continuing to fight, but it's tough. It's a tough fight.
Crucially, culverts that had been built to allow water to flow through the causeway had cracked to the point they could collapse and take the track out of service.
Due to the nature of this extreme environment, those culverts were folded upon each other, they were consuming it, didn't work.
To keep trains running, the cracked culverts were filled in. But what happened next was unprecedented. Blocking the flow of water created a startling difference in salinity, water level, and even color.
So the engineers had to come up with a different plan, a different solution that ultimately would enable the lake to breathe its water and allow railways to move.
In 2016, this clash with nature inspired another incredible feat of engineering.
So this is the brand new bridge that engineers hope will solve the causeways problems once and for all. The new pillars are driven 200 feet down, even though the lake's only 35 feet deep. The pilings themselves are a steel core covered in a special material to prevent effectively environmental damage, eroding and destroying the columns. See, as we pass underneath the berm here, this allows the railway to add and remove material to help flow control in between the northern and southern parts of the lake. The northern part's much saltier, so the water exchanges through. Wood couldn't make it, concrete couldn't make it, so hopefully this is the solution that will solve these problems from a material science perspective for the railway.
This watery wilderness baffled engineers for decades. But despite the struggle, the railway ultimately won.
This has got to be one of the most hard-fought pieces of railway engineering on the planet. Nothing but respect for the people that keep this line in service in such a tough place. Oh, it's what a cool sight to watch this actually happening on the Great Salt Lake. Oh, this is awesome. And it's truly impressive that the engineers have done as well as they have to keep this rail line running in such a harsh environment. It's magnificent. I love it.
The Great Wilderness Railways. Trains traversing the toughest terrain on the planet, presenting engineers with seemingly impossible problems, requiring pioneering solutions.
This has got to be one of the most hard-fought pieces of railway engineering on the planet.
To reach their ultimate destinations. Trains love flat terrain. Gradual gradients are fine too. But scaling a mighty climb in a short distance through dense wilderness is an engineer's worst nightmare. New Zealand's North Island is an epic wilderness of impenetrable rainforests and soaring volcanoes. It's a terrain that would be seemingly incompatible with building a railway. Yet taking on this rugged landscape is the main trunk line. In the late 1800s, engineers were trying to connect its two major cities, Auckland and Wellington, by train. But there was one spot on the route where progress reached an impossible impasse. Amongst the rugged, overgrown wilderness was the Central Plateau. Local railway expert Paul Mahoney is taking the railway to this challenging location.
I'm at Otorohanga Railway Station, about to get the train down to Raurimu. This railway was surveyed from the north and the south, but for 14 years, Raurimu was a sticking point for engineers.
But in 1898, it fell to engineer Robert West Holmes to conceive a plan to surmount the wild landscape. However, it wouldn't be as simple as carving a path through the untamed bush of Raurimu, as heritage advisor Karen Astwood is discovering for herself.
When engineers were trying to make a railway through this area, they had such a lot of trouble. It was a real nightmare. Coming down from the Central Plateau, there's a more than 400-foot drop, and there's no escaping it.
Faced with a distance of just 2 kilometres in which to negotiate the precipitous rise between the valley and the plateau, the gradient of 1 in 15 would be too steep for standard locomotives.
The only way to make it up that gradient in a train would be to use specialist trains, but the cost of maintaining those was simply too prohibitive. There was talk that the line might have to be rerouted. The government didn't want that. They'd already spent enough money on the project. Overcoming the wilderness here was seen as the lesser of several evils.
Even riding the rail link today, the journey is a reminder of what Holmes was faced with.
This was covered in a thick native forest. It's very rugged country. Here's the sort of forest they were working in.
With help from technology that Holmes could only have dreamt of, Karen is getting a bird's eye view of this uncultivated landscape.
This is really exciting.
And from the sky, the extraordinary solution that Holmes came up with can be viewed in all its glory. The Rowry Moo Spiral.
What we can see below is one of the most ambitious and brilliant pieces of wilderness engineering in the world. Here comes a train, so we're going to be able to see Holmes's masterpiece in its full glory.
Following an intricate route, the single track snakes its way around to lengthen the line at a shallow gradient.
The Rowry Moo Spiral is really impressive and complex set of elements, which is really compactly put together.
But Holmes' masterpiece was anything but straightforward. The spiral twists and tunnels under itself. Up first through a giant horseshoe curve and then a pair of tight quarter turns, before winding round on itself in a complete circle to reach the plateau. It extends a distance of just 2 kilometers as the crow flies to create a track an incredible 6.8 kilometers long. Seeing the spiral from Holmes' perspective reveals the curves close up.
So this is the start of the real climb. We're onto one of those tight curves. They're 150 metres radius, and we're on a 1 in 50 grade. This is real mountain railroading. They had to put this railway to the landscape, and it was very dense forest here, so they couldn't actually see very far to do the surveying.
A problem made worse by the treacherous terrain, which gave Holmes no natural vantage points to plot a route from above.
There was no way he could get to a high point to see how the land was set out. He had to do a lot of exploring to create a picture in his mind of what the terrain was like. So this is an amazing railway location achievement.
These days, engineers would carry out an aerial survey and simply take to the skies.
Wow, it's really incredible to see the spiral from this angle. You can really get an appreciation of what a masterstroke of engineering it is. All the loops and curves, even the small ones, were really critical because they lessened the wear and tear on the trains and on the track as well.
But mapping a route wasn't the only challenge that had to be overcome to pull off this audacious construction.
Okay, train is entering the first tunnel, which curves around, and then there's a really short gap, and it goes into the second tunnel.
So coming out of tunnel number 2, we're more or less halfway round the spiral now. Looking back, you can see just what rugged country this is.
Carving a path through the impenetrable forest, steep ravines and sheer cliffs had to be done by hand.
So the spiral was entirely constructed by pick and shovel and some dynamite blasting. And this is a high rainfall area. The workers lived in tent camps, and it was pretty tough going. What an achievement.
In 1908, the first train travelled down the Rowry Moo Spiral. almost 4 decades after the North Island main trunk line was first conceived. Finally taming what had seemed like an indomitable wilderness. Over a century later, it's still considered one of New Zealand's greatest feats of engineering.
This must have been so complex to try and lay out, and it really is just a tribute to Holmes's genius and also the engineers that he worked with. It's spectacular.
80 years after Holmes laid out the spiral, I was riding with the chief civil engineer of the railways, and he'd been involved with trying to improve the route of the railway ready for electrification. And the modern engineers were still not able to improve on George Holmes' spiral location. It's a masterly piece of engineering that survives to this day.
Wildernesses, vast expanses of some of the most grueling terrain on the planet, tackled by extreme railways, with courageous feats of engineering.
It's really incredible to see the spiral from this angle.
But imagine the challenge of building one of the earliest railroads in Britain. If you have goods to deliver, then the railway makes complete sense. That is, of course, if there is a railway that can be used. But in the wilderness, tracks can be hard to come by. Finding a way through could be a rocky road. In Devon, in the southwest of Britain, sits a huge expanse of harsh, magical and ancient landscape.
This is Dartmoor National Park, which is just shy of 1,000 square kilometres of amazing wilderness. It's full of ponies, rolling heathlands full of gorse, and its most famous export, granite.
And in the 1800s, that granite was in demand. With the British Industrial Revolution at full steam, buildings were getting taller, bridges were getting larger, and engineers were looking close to home for supply to meet the ever-increasing demand. As historical archaeologist Cassie Newland is finding out.
You can really see around here that the granite just sort of comes out of the ground. It's everywhere you step, everywhere you look, which is why people have used this resource in this place for thousands of years.
Dartmoor might have been full of granite for almost 300 million years. But in 1820, the enormous challenge would have been building a transport system to get the rock to civilization.
It's bleak, it's isolated, it is utterly treeless. You can go from frostbite to heat stroke in a blink. How can you build a railway here? What would you build it out of?
Entrepreneur George Templar decided he could defy the odds and build a railway to transport goods from his quarry at Hay Tor.
This idyllic little oasis is actually Hayter Quarry, and it would have felt incredibly different 150 years ago. We'd be surrounded by bustling men hard at work, drilling holes and blasting with dynamite to take vast chunks of granite out from the cliff walls. The air would be thick with dust. It would be completely unpleasant. Just behind me, if you can see the log in the pond, that log is actually the base of a derrick, a kind of crane that would have been used with the winch that you can see in the background to lift these huge blocks of granite. So you would turn this handle, and it would crank a cable, which would lift up the arm, your jib arm of your crane, which is just over here. And if you're very careful and don't fall in, it's this huge, huge length of wood with a socket at one end through which all your winching gear would pass, right the way down to the base over here, which would fit into a metal socket in the ground and allow you to pivot around to lots of different points in the quarry, lifting the stone that's blasted off from the side to places that can be worked, and also lifting it onto the wagons to take it away. So the challenge of Hayter is getting the granite out. But at 1,300 feet above sea level, with no other natural resources, it is an impossible challenge.
Templar had realised that building a track out of the quarry was the only option.
Like generations of Moormen before him, he looked to the ground beneath his feet and he built the railway from granite.
This engineering marvel born out of the ground is the Haytor Granite Tramway. Amazingly developed to transport the very granite that it was made of, from the quarry to a canal for distribution.
Now this rail here is the perfect place to see how skilled and arduous a job it is to produce a granite railway. Because using a chisel and a hammer, you've got to cut this lovely precise line right the way along your rail for the wagon wheels to run in. The one good thing about having invested all that time in creating a granite rail is you don't then need sleepers. The stone itself is so heavy it holds it in place. Now, granite is incredibly hard. The man-hours that go into taking out a slice of granite like this are incredible. And if you think you do that over 10 miles worth of railway, the labour is extraordinary. The first thing you've got to do is split your rock into manageable chunks. And you do that using a feather and tear method. And these slots here are remnants of that process.
The ingenious feather and tear method is still used today, though made much easier with the help of modern tools, as demonstrated by Dartmoor National Park employees Lee and Andy.
Well, what we're doing here, we're drilling a line of holes down the length of the granite where we want the split to be. To make the holes in the 19th century, they would have used a tool like this, which, as you can probably hear, is a fairly heavy piece of iron. It's called a jumper, so it acts like a drill. Well, we've drilled the holes along the granite slab now. The next stage of the process here is to use the feather and tear tools. Two types of tool here. We have this metal iron chisel, which is the tear in the process, and these two thinner strips of iron which fit down the side of it in the hole. Once you've got this arrangement in the hole, if you hit this on the top with a hammer, it will force it down and force the granite sideways. If you do that in each of the holes along the length, eventually the stress will cause the granite to split along the line we want it to. That's not going anywhere, so that's ready for the next stage. That's it. We have now successfully split the slab exactly where we wanted it to. Shows it's a very effective and quick technique, really.
This traditional technique leaves you with the perfect building blocks for creating your track.
That's like modular engineering, because when you've finished with your quarry over there, you can reuse this stuff. It's like a kid's train set. You just pick the bits of rail up, plonk them down on a wagon, pull it off on your carts to wherever you need it.
This astounding feat of engineering is made more impressive by the speed of its construction, precipitated by an important commission.
So as soon as George Templar had won the contract to build London Bridge, he had to get this railway in as quickly as possible. The quarry opened in 1819, and this railway was opened by 1820. That is an astounding feat of will.
But solving the challenge of building this railway is only half of this incredible achievement. As steam locomotives had only just been invented, Templar used the more common engine of the day, good old horsepower. The problem was how to avoid your prized equine engine getting crushed by a load of granite.
So gradient is always an issue for every railway. But here, where you've got just regular wagon wheels, running on grooves, cut in stone, it's a particular problem. Instead of the horses pulling the wagons, what they effectively have is the horses braking the wagons from behind, and up to 12 wagons, each of them carrying 3 tons of granite, being sort of slowly lowered down the hill on these rails. So you've got the horses behind, but for tricky bits where there's an incline or points, you've got a man with a stick, a 12-foot pole that he jams against the wheels as an extra brake. The whole thing is at the absolute limit of human skill and ingenuity. And the reason the horses went down was not just to break it, but to pull the wagons back up the hill from the other end. So it's all thanks to Templar's pragmatic solutions that the granite from the high tors can now be found in some of our most iconic buildings. Nelson's Column, the British Museum, London Bridge, and it's all down to this perfect yet simple railway.
It's another tenacious solution to reach into the wilderness. Wilderness, home to some of the world's most daring railways. Built by intrepid innovators overcoming the odds. From uncharted lands to watery vistas. Engineers are always pushing forwards, but sometimes they can be stopped in their tracks. When you're building a railway across the wilderness, and the seasons change, as an engineer, you never quite know the lay of the land. Covering an area greater than Western Europe, the Tibetan Plateau in Asia is the largest and highest plateau on Earth. With drifting sand dunes and alpine wetlands, temperatures swing from a bone-chilling -40 degrees in the winter to a sweltering 30 degrees in the summer. It's a treeless and windy wilderness. On the face of it, this is the last place on Earth for a railway. But the Qinghai-Tibet Railway has taken on this challenge. For a century, China had dreamt of connecting with the inaccessible region of Tibet. In 1974, work on a railway began at Xining. Cutting across the rugged northern edge of the plateau to Golmud. But when engineers tried to head south to Lhasa, they encountered a seemingly impossible obstacle. 550 kilometers of unstable terrain, with a permanently frozen layer below the surface known as permafrost. Senior engineer Mr. Jinshang Wang was part of the team in charge of finding the solution.
Permafrost is a mix of soil and sand bound by ice with a temperature that remains below zero for at least 2 years. If the frozen soil is always below zero, it will provide a solid and stable foundation for buildings above it. However, the surface layer can melt and its load-bearing capacity can decrease, damaging all the architecture above.
Without solid land to lay a track on, engineers had to find an innovative solution.
So we built a bridge instead of laying tracks.
This is the Qingshuihua Bridge. At 11.7 kilometers long, it is the longest bridge over permafrost in the world. But building it was a feat of remarkable endurance. Using techniques derived from decades of research, engineers had to dig deep enough to reach the solid base below.
So there must be 4 piles beneath every pillar. The pile foundations are 20 to 30 meters deep.
To reach those depths, a rotary digging machine is used. The holes are then filled with concrete. But as heat is released by a chemical reaction during the concrete mixing process, the danger is damaging the permafrost. So the work needed to be completed during the harsh winter months. But to set and strengthen, concrete must be kept above 5 degrees, which means it has to be heated before it's poured. So chemicals are added to the mixture to help speed up the setting process and safeguard the permafrost. This phenomenal bridge spanned the most difficult section of the Qinghai-Tibet Railway and enabled engineers to finally complete their journey across the plateau.
Building a railway under extreme weather conditions on the Qinghai Tibet Plateau is 10 times more difficult than building a railway on normal solid ground.
It took an army of more than 600 medics and 17 oxygen stations to support the construction team. Reaching altitudes of over 5,000 meters means that oxygen is 45% lower. Today, just traveling the route gives a real sense of the conditions that the workers faced. Even passengers on this highest stretch of rail need to have access to oxygen. Completed in 2006, the railway was mainly used by tourists visiting the once isolated region of Tibet. Today, it's a vital part of everyday life for the locals, with the number of trains almost doubling in just over a decade. But none of it would have been possible without the Qingshui-Hua Bridge.
Being part of the operation and management of this worldwide engineering project is my glory and my duty.
Permafrost might be a formidable opponent, but around the world, railways must cross many different landscapes. And one that presents an altogether different challenge is a woody wilderness. In the late 1800s, fueled by the gold rush, the demand for timber across North America was sky high. Thick pine forests on the western slope of the central Sierra Nevada wilderness offered an abundant supply. Horse and oxen were the usual method of transport, but to meet demand, locomotives with their superior power began to appear. But getting them through thick forests was far from easy. Engineer Chris Potts is at the site of a once prolific logging operation.
This is the Sugar Pine Railroad, located in California's Sierra Nevada forest. And these surroundings are what would be typically seen in the early logging camps. These tracks here are actually quite modern, made of steel, sturdily fixed into place, and well-maintained. The difference is that the early railroads would have had no such luxury. Earlier railroads were made of the logs they milled. The tracks would have only ever been temporary.
Quickly laid temporary tracks would weave their way through the trees. The track's tight curves and makeshift nature were a recipe for disaster for the recently introduced rod locomotives. These huge trains were powered by pressurized steam, with their horizontally mounted pistons driving only a single set of wheels. All the power from the engine concentrated in a small area meant poor traction and a limited ability to climb gradients.
This is a rod locomotive's worst nightmare. They could only travel about 4% grades at their max, and this right here is about 12%, almost 3 times as much as a rod locomotive could usually go on. With the rough terrain, the tight curves, and the steep grades, rod locomotives would have a hard time making it here.
But it's not just the terrain that the engineers were battling with.
When the rod locomotives went down the track, the action of the piston moving back and forth would have easily tore the tracks right out of the ground. If locomotives were going to make a positive impact on the logging industry, the rod engine would have to be completely rethought.
And in 1877, entrepreneurial logger come inventor Ephraim Shea proposed a solution with the introduction of his radically redesigned locomotive.
This is incredible! I'm riding the number 10 Shea, the largest narrow gauge Shea ever built. Standing up here, you can truly appreciate the power. the steam, the heat of the fire, and the pistons moving up and down. What a feat of engineering. Absolutely incredible.
This is a Shea Lima locomotive, and it's impressive beyond its mighty power.
At first glance, you'd be forgiven for confusing the Shea with a rod locomotive, but actually it was a revolution in design. It completely transformed the locomotives for the logging industry. Wilderness like this would stop any rod train in its tracks, but not the Shea.
The key to Shea's design is that instead of using rods to power just one set of wheels, it uses gears to share the power between 6 sets of wheels. It's a fundamental change that transforms how a locomotive uses its power and gives the Shea its unique appearance.
What a monster of engineering. This is how it works. There are 3 giant pistons, and these massive pistons work in a vertical direction. As the power generated by the steam from that boiler is transferred into this gear train, it is sent down to the bevel gears, and these gears work with a 2-to-1 ratio, where the smaller gear spins twice as fast as the larger gear. And the way it works is it takes that speed from the smaller gear and transforms it into torque, meaning that this train can go up 14% grades, unheard of for trains of its age, and can take huge loads across huge distances. There's a bevel gear on each one of these wheels, essentially making it a 12-wheel drive. Pretty cool.
By realigning the cylinders and gearing the power to each set of wheels, the Shea also had increased traction and would be far better suited to the demands of the challenging logging landscape.
So one of the key differences here is that this train operates with 3 vertical pistons, meaning that it was a lot less destructive than the rod locomotives of its time, where they operated with a horizontal piston, meaning that it was less destructive to the tracks.
After its introduction in 1878, the Shea locomotive was an instant success story, enabling these relatively small engines to move heavy goods at low speeds over rough terrain. Over the next 10 years, more than 300 Sheas were produced, totally transforming the logging industry.
The Shea train was perfectly equipped to brave even the most challenging of wilderness. This is an incredible feat of engineering. Just the sheer power. I love it.
For centuries, railways have carved paths through the world's most unforgiving wildernesses. Through exceptional creations.
It's spectacular, and you don't find this type of thing in many places in the world.
It's rainforest railway engineering at its world's best.
And cutting-edge solutions.
Someday they'll have to build a train on Mars or the moon or whatever, but this is about as close as that gets on Earth.
Engineers continue to succeed, creating impossible railways.
Engineering versus the wilderness, I think engineering won.
Many of the world's greatest railways have defied nature, overcoming its most difficult terrain. Whether scaling sheer heights or navigating dense forests, engineers have managed to carve out routes to create the most epic lines imaginable. But crossing chasms tests them to their limits. From ferocious rivers to remote wind-swept valleys. Uniquely engineered bridges crucially keep the world connected. But each of these crossings throws up individual challenges that are often seemingly impossible for railways to overcome.
When you see that view, you can understand why it was so difficult to develop transport back in the 19th century.
The Rosa line was very difficult to construct because this valley is a close, narrow valley with steep hills.
Well, the key challenge is the tidal range. The water flows in and out of a quite constricted channel very fast.
But arguably the biggest obstacle facing bridge engineers is a hidden one. Bridges can help the railway overcome almost anything. They can conquer dizzying heights, span the longest lengths. But when it comes to crossing shaky ground, you need to think carefully before you continue. Located on the notorious Ring of Fire, New Zealand's brooding volcanoes are a stark reminder it sits squarely on a major fault line, where the Australian and Pacific tectonic plates collide. Here, the devastating effects of earthquakes are an ever-present threat. Heritage advisor Karen Astwood has travelled into its rugged interior to see how engineering played its part in keeping a vital railway safe from seismic shifts.
What I'm approaching now is one of the North Island Main Trunk original tunnels. When the line was constructed in the early 1900s, it became incredibly important because it connected Auckland and Wellington, which is the North Island's two major cities.
But by the 1960s, this particular section of the main trunk line in the Rangitiki district was putting the route in jeopardy. Many of the tunnels built were in danger of collapse.
Upgrading this section simply wasn't practical. The unstable ground meant the tunnels weren't feasible to strengthen, and neither was creating new ones.
Instead, engineers came up with an ambitious plan to reroute the original line, known as the Mangaweka deviation. But in the way lay what appeared to be an insurmountable obstacle.
This is the Rangitiki River, one of New Zealand's longest and most spectacular rivers.
Today, Karen's taking an entirely different form of transportation.
Hi, Karen.
Hey, I'm good, thank you.
To get an idea of the true scale of the problem.
I'm really looking forward to this. It's going to be great.
You can jump on the raft here.
The river here has carved a massive gorge. You can really get a sense of why the original railway line didn't go this way. So that's why they went with the tunnels. It was only in the late 20th century when they had the better technology available that they even attempted to cross this gorge.
And even then, it would still take an extraordinary feat of engineering ingenuity to do it.
And this is what I've been waiting for. Here it comes. This is the South Rangitiki Viaduct. It is immense. What an amazing structure. So impressive.
Opened in 1981 and measuring a staggering 315 metres in length, the mammoth six-span viaduct carries a single track across twin-legged piers, a vertigo-inducing 76 metres above the river.
Wow.
But to see what makes this bridge truly revolutionary, you need to look much closer to the ground.
When designing the South Rangitiki Viaduct, engineers had to consider the earthquake conditions it needed to operate under to keep the critical North Island Main Trunk line functioning.
It was the groundbreaking work of eminent earthquake scientist and engineer Dr. Ivan Skinner which provided the answer.
At the time the Mangaweka deviation was being planned, seismic engineering technology was in its infancy. So the designers of the South Rangitikei Viaduct had to come up with a completely new solution: base isolation.
The first of its kind in the world. The bridge's innovative design features energy-absorbing dampers in the foundations, which allow it to step from side to side when a tremor hits.
Okay, so we're just putting together a really basic demonstration to give you an idea about how base isolation works. To begin with, we've got a shake board, which is going to mimic the horizontal forces of an earthquake. Now, usually you'd build your bridge straight onto the earth. With the South Rangitikei Viaduct, however, we've got the foundations, and then we've got the base isolation, then we've got the pier.
Unlike traditional bridges, the foundations consist of two sections. One built into the ground and the other fixed to the bottom of each pier. At the base of each pier sits a set of rubber pads, which act to absorb a portion of the energy created in the event of an earthquake.
So these tennis balls are standing in for the flexible bearings or pads that are in the base isolation. And this is a platform that the bridge pier is going to sit on. Okay, so now that we've got the foundations sorted out, we're going to build our piers. This is just a standard old bridge, build it straight into the ground, onto the foundations, and here is a pier from the South Rangitikei Viaduct. But to show you the full effect of how the base isolation works, I've just got to duck off and get some water.
Rather than rigidly fixing the bridge, the base isolators effectively separate it from the ground for greater flexibility.
Okay, so here comes an earthquake. And as you can see, the one straight into the ground is absorbing all of the energy from the earthquake, so it's more likely to fail and the bridge collapse. While the South Rangitikei Viaduct, it's not absorbing as much of the earthquake forces, so it's less likely to fail in the event of an earthquake.
Under most circumstances, the bearing pads absorb enough force to keep the bridge structurally intact. But in a major earthquake, the pier can lift up by as much as 13 centimetres, allowing it to step from one leg to the other, preventing a catastrophic collapse.
And that's the genius of base isolation.
Every day, Ivan Skinner's inspired innovation enables trains to traverse the length of New Zealand's rugged North Island, keeping the country moving even when experiencing the most terrifying tremors.
Engineers weren't going to let earthquakes stop the railway. This is an ingenious piece of engineering, and I love it.
Many of the world's most impressive bridges were built to carry the railroads. Ingenious structures spanning the deepest chasms. Building bridges is a fundamental part of railway engineering, but arguably the biggest challenges are posed by the elements. When the weather's on your side, riding the railway is a sunny proposition. And when it comes to bridges, clear skies can make for pleasant crossings. Unfortunately, Mother Nature doesn't always play nice, and the consequences can be disastrous. Southern France's rugged Auvergne region isn't the most obvious place to build a railway. But at the end of the 19th century, transporting wine from the region's vineyards to the capital, Paris, became a priority. Forming a natural blockade, however, was the Massif Central, a sprawling landscape of imposing peaks, deep gorges, and famous for its strong winds. Historian Patricia Rocher is taking to the skies and taking on the notorious turbulence.
Wow.
To get a bird's eye view of why plans to build a new line had hit the buffers.
When you see that view from the plane, you can understand why it was so difficult to develop transport back in the 19th century.
For years, engineers had sought to conquer one particularly problematic obstacle: the immense Throttle River gorge.
The valley is very deep and very large. You had another difficulty, which was the wind. You know that wind makes tall buildings sway, and in a valley, the wind is stronger. So here in Garabie, it was really a challenge.
To combat the elements and bridge the valley would require a feat of engineering ingenuity: the breathtaking Garabie Viaduct.
Wow, what a wonderful view. It's really fantastic.
At 564 meters long and 122 meters high, upon its completion, Garabie was the tallest and longest railway bridge the world had ever seen.
You know, the first time that you come here in Garabie and you see this enormous structure, it's really a mind-blowing experience.
The iconic design of the Garabie Viaduct was the work of one of the 19th century's most celebrated engineers, Gustave Eiffel.
It was an exceptional site to build something, and that's why Eiffel was contacted, and he said, "Okay, I will do something here."
Eiffel's solution to withstanding the gusting winds is today being viewed up close by the maintenance team tasked with inspecting this mammoth structure. It's one that would go on to earn him the nickname, the Magician of Iron.
The one factor was very important. He used structures with holes to let the wind go through. You can see on this viaduct the crosses, you know, and it's very typical of Eiffel style.
Instead of thick, solid girders, Eiffel used smaller, crisscrossing wrought iron beams with thousands of triangular gaps. His inspired design dramatically reduces wind resistance as it's buffeted by the powerful gusts at Garabie.
Just let me explain. You see here, the wind have no space to go through the structure and it fall down. Thanks to the hole in the structure, it's okay. You see, the wind can go through it.
Despite its lightweight appearance, the Garabie Viaduct was designed to carry a 400-ton train and built to last. The 165-meter-wide arch was constructed from both sides, as cranes at each end extended it piece by piece until the two halves were joined. Metal structures expert François Millien
On fera une pause, ouais, à ce niveau-là, là, au troisième palier.
Is part of the fearless team responsible for ensuring the bridge continues to stand the test of time.
I remember the first time I was here, it was so impressive. Nobody can forget this.
Taking 5 weeks to complete, each of the bridge's crisscrossed beams and 600,000 rivets are inspected for signs of wear.
Yeah, of course, you know, when a train across the bridge, you know, we can feel all the vibrations. We just need to look if we don't have some fissures or cracks.
After another clean bill of health, this masterpiece is still standing strong against the brutal battering of the wind. Eiffel's little-known masterpiece of railway engineering remains a stunning example of his signature style that would later inspire a Parisian icon, the Eiffel Tower.
It was a great achievement. This one is special because everybody in the world knows the Eiffel Tower, but they don't know this viaduct.
We still are very proud of this viaduct. It's a special feeling to see such a structure in the air, in the middle of the countryside. This viaduct is really a celebration of French engineering.
railway crossings. Engineering marvels connecting some of the world's most thrilling journeys. Requiring unique designs and ingenious thinking. Historically, bridges have been built from many different materials, even in the most extreme of locations. Moving trains across mountains is never an easy task. To overcome the obstacles in your way, you'll normally need to build some bridges. But crossing heavy trains over vast valleys requires the right materials. And if what you've got isn't strong enough, you'll need to think again. Home to the towering Alps mountain range, Switzerland's impenetrable peaks would make train travel impossible. Were it not for the ingenuity and resourcefulness of its railway pioneers. Nowhere are the challenges they faced more obvious than the spectacular Rhaetian Railway. This iconic network of 10 lines clings to the steep slopes and valleys of the Swiss Graubünden canton. Today, bridge specialist Carl Baumann is taking to the tracks en route to a spot where early 20th century innovation helped conquer this most mountainous terrain.
Well, the network of Rhaetian Railway is about 400 kilometers long. We have 600 bridges, which have a length of 15 kilometers altogether. Makes about 4% of the whole net is over bridges. It's really special.
At its heart lies the Arosa Line, a 26-kilometre single-track railway which climbs a dizzying 1,000 metres through the Schanfigg Valley. Carl's destination is Langwies, where the forbidding alpine setting presented rail engineers with what seemed like an impossible obstacle to overcome.
The Arosa Line was very difficult to construct because this valley, which is called Schanfigg, is a close, narrow valley with steep hills.
To make matters worse, here at Langwies it also has to cross the vast River Plessia Gorge.
Here the line changes from the left side of the valley to the right side of the valley, and in a height of about 60 meters above the riverside.
For trains to cross that valley would take a feat of engineering on a truly epic scale. The daunting task fell to civil engineer Hermann Schursch. He not only needed to design a structure strong enough to span the huge chasm, it would call for a groundbreaking approach to how it was built too.
In the beginning of the century, most of the bridges were masonry bridges which are built out from stones. And here between Chur and Arosa, we have no such stones.
Given the steep terrain, transporting large sections of solid steel was out of the question.
Steel is not possible here because we had only the possibility to bring up 8-meter-long elements.
The solution was the mighty Langwieser Viaduct. Constructed from a material which had never been used to build a railway viaduct on this scale before. Reinforced concrete. At 284 meters long, with a central arching span 100 meters wide. When it was completed in 1914, it was the longest concrete railway bridge ever constructed.
Well, Langwieser Viaduct is in my eyes the most impressive railway bridge, and it's one of the most interesting engineering construction when you look over the whole world. Of course, this is a very innovative bridge because it's a concrete bridge. Concrete with steel inside was a new material in that time. It's very modern construction also in sight of today.
To build a bridge strong enough to sustain the weight of trains across the valley in a single arching span, Schurch embedded steel within the concrete members of his structure. By reinforcing the concrete in this way, he could make use of both materials' strengths. Steel to resist tensile or twisting forces, and concrete to resist compressive forces.
It was completely new design at that time.
Using a huge framework of wooden scaffolding for support, up to 200 men toiled on the project, ensuring its completion took just 2 years. Thanks to the vision and skill of the men who built the Langwiese viaduct, reinforced concrete conquered the giant gorge.
It's very impressive, and it's very great testimony to engineers of 100 years ago.
And changed the way rail bridges were built forever in the process.
When I stand here on the edge of Langwiese Viaduct in Langwiese, for me it's a very impressive construction. I'm very proud. It's a work of art, of course.
Across the world, pioneers have engineered new materials to create crossings. But in other locations, resources may be abundant, but the design takes some inspired thinking. When it comes to building bridges, using piers and foundations is normally a winner. But what happens when there's water in your way? Tides and currents can make things tricky. Meaning the only way to cross is to take your bridge design back to the drawing board. In the 19th century, engineers faced the challenge of building a faster route connecting London and Dublin. In order to connect the two capitals, a new rail line would be needed that would run along the north coast of Wales. But to achieve this ambition would involve bridging a deceptively difficult stretch of water. The gaping Conway River estuary and its complex tidal flows. The obvious place for a crossing was at the river's narrowest point, where Conway's imposing castle had been strategically built around 600 years earlier. But as civil engineer John Chilton appreciates, turning the idea into a reality would test engineers to their limits.
Well, the key challenges for building a bridge in this sort of situation is very fast-flowing river. The tidal range means that the water flows in and out of a quite constricted channel very fast.
Adding to the titanic challenge, it would need to bridge the entire river in a single self-supporting span, a feat seemingly impossible for the technology of the 1800s.
If the engineers were going to put a bridge across at this point, then they would have to have a particularly revolutionary solution to take these heavy loads across.
Their answer was the groundbreaking Conway Railway Bridge. The first box girder bridge ever constructed. Complete with formidable towers designed to blend seamlessly with its medieval neighbour. This pair of wrought iron tunnel-like structures weigh in at a massive 1,320 tons apiece. And stretching 129 metres across, when it opened in 1849, it was the longest single-span rail bridge in the world.
The key thing here is that you're taking the railway bridge to much larger dimensions. It certainly was a groundbreaker at the time.
It was the brainchild of two of Victorian Britain's most eminent engineers, Robert Stephenson and William Fairbairn. To eliminate the need for central supports, Stephenson's inspired idea was to carry trains through his bridge, rather than over the top of it. But the size of the span needed would push the boundaries of Victorian engineering like never before.
To show the principle of a girder, we've got 2 piers of the bridge here. We have a girder, this piece of paper, which is very thin and wide. And if we put it across between the piers, it sags and won't even carry its own weight. The strength of the girder depends principally on its depth.
To construct a girder strong enough, Stevenson and Fairbairn experimented with different shaped tubes.
So the circular section already holds its own weight, and it will carry this little pot at the bottom here. I'm going to add some pennies to demonstrate how the beam works. 1, 2, 3, 4, 5, 70, 71, 72. And as you can see, the tubular beam has failed by crumpling.
With only a small point of contact between beam and piers, load stresses cause it to squash at the ends.
So now we're going to take this rectangular tube and see if it outperforms the circular tube, which failed at 71 pennies. 72, 73, 74, 75, 101, 102, 3, 4.
Having a larger surface area in contact with the supports each side of the river meant Stevenson and Fairbairn's box girders could carry significantly more weight over a longer, single span. But overcoming the monumental challenge of crossing the River Conway didn't stop at the bridge's design. Constructing the enormously heavy spans in mid-air over the water wasn't an option.
If you have the high tidal range and you have fast-flowing water, it makes it difficult to put temporary supports in the channel.
Instead, its engineers turned to nature and ingeniously turned the Conway's treacherous tides to their own advantage.
The girder, made of wrought iron sheets and angles riveted together, was constructed on a beach nearby between the high and low tide marks.
Once complete, large pontoons were floated underneath so it could be towed into position and lifted into place with hydraulic pumps.
The high tidal range was actually used for the benefit of the construction process. As an engineer, I absolutely admire the teamwork that went into building this innovative bridge.
For its time, the Conway Bridge was a radical piece of railway engineering. By introducing the new box girder technology, it pushed the boundaries of what was thought possible and changed the face of bridge building forever.
The Conway Bridge certainly moved the technology forward because this form of bridge construction has gone on to influence the design of long-span bridge beams worldwide.
And this groundbreaking feat of ingenuity is still part of Britain's busy rail network today.
The Conway Bridge is a magnificent achievement. The fact that it is still standing here after 170 years is a testament to the quality of the Victorian engineering, and this certainly has stood the test of time.
Over centuries, pioneering engineers have built some of the world's most impressive railway crossings, making it possible for trains to conquer deep valleys, scale harsh mountain terrain, and cross wide tidal waters. But some of the most inspiring structures have been built from the very loads that trains travelling across them once carried. Sometimes crossing chasms can be the least of a bridge builder's problems. If you're working in the wild, getting materials to site can be a real slog. And if all that dragging and lifting gets too much, there might just be an answer that's closer than you think. At the start of the 20th century, the global market for timber was sky high. While Canada's densely forested Vancouver Island offered apparently endless resources to meet the demand, Transporting vast loads of lumber from this remote spot to the mainland and beyond presented an impossible challenge. A problem islander and master carpenter Gord MacDonald understands well.
This is Cowichan Bay, and Cowichan Bay is really the gateway for logs for this island, and it has been for centuries. It's getting them to here is the tough part.
In 1911, a railway was commissioned to carry wood from the logging camps to the coast, but building it would prove to be anything but easy.
100 years ago, you can just imagine how difficult it was to build in this sort of geography. Vancouver Island is very up and down, these long inlets that cut for miles and miles inland.
After extensive surveys, a route was finally chosen. One which left engineers facing what seemed like an impassable obstacle. The plunging Coxilla River Gorge.
Even on a summer day like today, you can hear the river below. And in winter, the water just chucks it down this valley, along the riverbeds, through almost impenetrable forests.
But trees had brought railway builders to the island, and it would be trees which provided a solution to bridging the huge ravine.
Once the decision was made to make a crossing, then the choices were really timber bridge or steel bridge. It's just sensible that you would prefer to use materials which are locally available.
Conquering nature with the simple resources on hand would take a truly remarkable feat of engineering. The monumental Kinsole Trestle. Standing 44 meters high and spanning 188 meters in length. The Kinsole Trestle took an incredible 1.2 million board feet of timber to construct, making it one of the largest wooden bridges in the world.
I must say, even though I've been here hundreds of times, it always is a real treat to come back. It's such a great bridge.
The wooden trestle was a vital part of Vancouver Island's valuable logging industry for nearly 60 years.
The Kinsole is really a unique bit of engineering. You've got this quite ambitious crossing, the deep side here, complexity of the shape.
A problem made worse each spring as the river levels swell with melting snow and ice, putting the timber to the test.
You can tell just by looking at it that it was really built to perform heavy work. There's a section of the bridge which is quite long and has to be kept up above the highest water. That section of the bridge has to be entirely self-supporting. I can't build in the in-canal section or in the river section because, of course, it would just be swept away.
To see just how the wood was engineered to conquer the river requires burrowing to the very heart of the bridge.
All the bears around here are vegetarians, I think. You should be reasonably safe. So where we are now is down in the very working guts of the trestle. We're just making our way out into the howe trusses.
First patented by American bridge builder William Howe in 1840. His ingenious design made it possible to build bigger spans using wood, something in plentiful supply here.
Howe trusses were great for these logging bridges because not only did they use a lot of wood, but you could use relatively small pieces or short pieces of wood.
In a truss, the three sides work together to give it strength. In a howe truss, the diagonal wooden beams leaning towards the center of the bridge are in compression, while the vertical metal poles are in tension.
So generally in the web of the truss, the timber is doing what it's best at. It's working hard in compression. The other big advantage of a truss like this is that it's also capable of a great deal of work over that long span. So it can carry a heavy load above and make a big crossing.
Today, Gord is going to check just how well they're holding up after almost a century.
So this is a tool called a resistograph, and it's a very slender drill. And as the drill advances, the onboard computer takes measurements of resistance. And we know that resistance is an indicator of wood strength.
Boring into the timbers at key locations reveals if they are sound or suffering from decay.
Imagine that that scale represents the path of the drill bit. And these peaks are measurements of high resistance, and the flat spots like that, that's probably the very center of the tree, the pith, will be less resistance. So, clean bill of health.
Although standing strong today, when the bridge closed in 1979, it quickly fell into serious disrepair. And in 2006, it was set for demolition. But after 4 years of painstaking restoration, the trestle was reopened as the centerpiece of one of Vancouver Island's most popular tourist trails.
People come from all over the world to see the bridge. They get an insight into just that age in the development of the West, when no task was too big and no undertaking too formidable.
And nearly 100 years after its completion, the Kinsale Trestle remains a towering achievement in rail engineering.
These sorts of bridges were just they're just a critical part of the railway, getting things from A to B. And one of the reasons we love them so much is because they just speak to that challenge overcome.
The world's engineers are continuously pushing boundaries. And in the 21st century, there's one mega bridge in the making that will be capable of conquering all. India. Home to some of the world's remotest communities. None more so than a region within Jammu and Kashmir, bordering Pakistan at the foothills of the Himalayas. And it's here that a record-breaking railway project of epic proportions is underway.
The region around Bakal and Kauri is very, very remote, and it's very difficult to get around there. And so for a long time, there's been this will or this need to create a railway link.
The Kashmir Railway project is a 345-kilometre line that will connect communities amidst some of the most hostile terrain on Earth.
That rail line has to go through tunnels and above bridges because of the really mountainous topography that we experience in the Himalayas.
But in its path to completion lies a ferocious obstacle.
One of the trickiest segments of the entire line is where the railway has to actually cross over the river Chenab, and that's because the gorge is very, very deep there. So the distance from where the railway line is down to the surface of the river is over 300 meters.
The only way of spanning this enormous chasm is with the world's highest railway crossing, the audacious Chenab Bridge. At a staggering 1,315 meters long and towering 359 meters above the river, once completed, the Chenab is set to be a true giant of engineering.
The Chenab Bridge is a record in the making because once it's finished, it will be the highest railway bridge in the world.
But the most crucial phase of this epic project so far has taken place more than 100 meters below the valley's edge, preparing its foundations. No mean feat for a bridge of this magnitude.
The bridge itself is only as strong and stable as the foundations upon which it's built.
Engineering geologist Phil Ward has first-hand experience of dealing with the challenges facing the construction of the Chenab Bridge, not least because of its remote location.
When I first visited the site, it was a 6-hour jeep drive from Jammu up to the bridge site. The access roads were subject to landslides. The Chenab Bridge is crossing the Chenab River at a location where the slope angles are particularly steep. And surrounding the area of the bridge, there's a lot of evidence of big landslides, so slope instability along the river gorge.
It took 2 critical years of boring into the steep slopes to analyse the condition of the rock before engineers were satisfied that the bridge foundations could be constructed. Then, the colossal process of stabilising the rock faces began.
These were the largest cut slopes I've ever been involved in, and a great deal of rock had to be excavated, and very, very large numbers of rock bolts had to be installed to stabilise those cut slopes.
Rock bolts are formed from grids of steel bars, some up to 40 metres in length, that are driven into the rock face and secured in position. Once inserted, the bolts help stabilise and strengthen the valley's walls, creating a surface that's secure enough to build on.
These reinforced the rock mass and gave us assurance that we could provide an adequate factor of safety on slope stability.
Over a decade since its conception, the vast gorge is almost ready for the arch to span the river. However, this project still has years ahead of it, and many more obstacles to overcome before the bridge and this ambitious railway line is complete. The giant arch will need to withstand all that this volatile region can throw at it, from earthquakes to destructive winds and monsoon rains. But once complete, this monumental structure will dwarf the Eiffel Tower and set a new benchmark for mega bridges around the globe.
For me, this has been one of the most exciting projects I've ever worked on. The scale of the project is mind-boggling in actual fact, and it always amazes me every time I visit the site as I come around the corner on the access road and see these massive rock faces dwarfing the tiny little vehicles that are traversing the faces.
This project is testing engineers to the limit and will surely continue to do so. Meanwhile, the world watches challenge after challenge overcome.
I think it is so fascinating watching the progress of a record-breaking bridge like the Chenab Bridge. And I also think it's a real jewel in the crown for structures in India because it's had so many different complex challenges solved that it will almost set a precedent. Once this bridge is finished, I think it'll be one of the most impressive bridges in the world. It's a really, really impressive structure.
Since the birth of the railways, bridges have opened up the world to trains. Allowing them to cross seemingly unconquerable chasms.
I hope at some point in the future I can travel across the Chenab Bridge and feel privileged that I was involved in the design.
Thanks to inspired solutions.
The base isolation used in the South Ringatike Viaduct was completely innovative at the time.
Engineers continue to build their impossible railways.
Every time we push a boundary, we then aspire to push that boundary even more, to break that next record.
As they make their epic journeys across the continents, railways continue to push boundaries ever further. Inspiring engineers to find new ways to tackle all of nature's extremes. But there is one challenge that raises the bar higher than any other. The mighty peaks and sheer cliffs of mountains. From their treacherous, winding terrain
Simmering features grades and curves that has never conquered before by a railroad.
To impossible inclines for trains.
The steeper you make it, the bigger the train you need in order to overcome this incline.
And passengers to overcome.
The challenge here is because the natural wall is more or less vertical, so we have to find a way.
It was the challenge of one epic climb that faced Swiss engineers in the mid-1800s. Inclines are often a test for trains. But the struggle to overcome them is always worth it. The trouble is, when they do make it to the top, of course, what goes up still has to come back down. The Swiss Alps, part of the largest mountain range in Europe, and home to some of its highest peaks. For centuries, their alpine vistas have been attracting tourists with a sense of adventure. But with their unrelentingly steep terrain, these mighty mountains are a railway's most formidable opponent. Railway technician Stefan Reichel is travelling on the Rigi Railway to see how adaptations to the track and the engine made it one of the first railways to take on a seemingly impossible mountain climb.
Look at that sunshine. Look at this Rigi Mountains. I love it. And now you can hear the engine starts working hard because it's very steep on Rigi. And now listen to that noise. The fireman is doing his work. He needs to shovel 500 kilograms of coal into the boiler up to Rigi Staffel.
Today, this train is one of the most popular tourist trains in Switzerland. But in the early 1800s, the only way to reach the vertiginous heights of Mount Rigi was on foot or by carriage. In 1869, engineer and locomotive builder Niklaus Riggenbach was commissioned to connect Witznau on the shores of Lake Luzerne with the summit of Mount Rigi, 1,798 meters above sea level.
What Riggenbach really found was just working up here was hard.
Having seen trains slipping and losing traction on other railways with shallower gradients, Riggenbach knew his solution would require radical rethinking. The railway would have to climb 1,115 meters in just 5 kilometers.
Now we are at the steep gradient, the boiler is now in level, and the engine couldn't hold on by pure adhesion. So it has to grab to something. Like children would slide down a slide, the engine would slide down here if it's pure adhesion. So if children go backwards to slide, they grab onto something. And Riggenbach did the same. He used something to where the engine could hold on, or could grab on. So he invented a third rail between the normal rails.
Riggenbach designed a toothed rack rail between the running rails. A cogwheel was added to the center of the wheel axle to mesh with this rack rail and give the train traction.
And this is how the cogwheels inside merge into the third rail of the rack system. And this is how the engine gets a hold.
In 1871, the Rigi Railway was the first rack and pinion railway in Europe to conquer a mountain.
And now listen to that noise. This is why you sit directly behind the engine, because you have to enjoy a working engine. And you can feel the engine moving by that rattling and by now speeding up. This is only about 6 miles per hour, but it sounds like we're going 100 miles, and it's nearly you're going up. It's like Riggenbach built a stairway to heaven.
Taking nearly 2 years to complete, Riggenbach had finally brought this mountain to the masses. And today, as many as 500,000 people a year make the journey to the summit.
Up here, this is one of the best views I ever have seen in my whole life. I have been to many mountaintops, but none of that had that panorama as Rigi. Now I know why Riggenbach conquered the mountain with that tiny railroad, but up here it's only half of the problem.
Having managed to get the tourists to the top of the mountain, the elevated incline presented Riggenbach with a challenge of equally tough proportions. With a 25% gradient, the rate of descent was creating too much stress on the boiler and band brakes of his locomotive, as well as damaging the track.
Usually on an incline, the most railways encountered a very problem because the wear on the brakes was so high that the brakes could fail. And so you roll down without any brakes and could derail, and many accidents happen.
For a train full of passengers, this could have been catastrophic. Riggenbach needed to find a way to slow the train down.
Rigi was too steep for normal braking systems, and so he decided to use a different brake system, a brake system which could not fall apart.
Riggenbach surmised that if the engine was strong enough to push the locomotive and carriages up the mountain, then it should be strong enough to slow it down on its descent.
And now we go down by Riggenbach. And this is what Riggenbach really invented, is the brake system. What we hear right now is air is moving into the cylinders and it's pressed out by the silencer next to the stack. Did you hear it? The chugging noise has changed. It is now a noise of compressed air.
When the engine is running, the Riggenbach air valve is switched, so that exhaust will leave by the blast pipe. To apply the brake, the throttle valve is closed and the Riggenbach air valve is switched in the opposite direction, allowing the pistons to pull clean air in. The air becomes compressed in the cylinder, acting like a cushion and slowing the pistons down, which in turn slows the train.
Personally, I think this is the best dynamic braking system for steam locomotives you ever can have, because it has no additional structural details which need to be special. You can build it in any steam locomotive of any type, and it's an absolute valuable brake system because it applies the brake pressure by itself. As faster the train goes, as harder the brake is acting.
The Rigi Railway became the highest standard gauge railway in Europe.
Being here at Rigi is something very, very special because it's the oldest operating cock rail in Europe. It's an absolute awesome ride upwards and then going down with the Riggenbach brakes, smooth, soft. That's the invention we are all for here. This is what makes the genius of Riggenbach.
The Great Mountain Railways, cutting their way through treacherous terrain to complete their incredible journeys. But every mountain range throws up unique challenges, some seemingly impossible to overcome. Given enough firepower, most ordinary trains can climb a hill. But no matter how hard you try, extra muscle can only get you so far. Huh? Ecuador. From the Pacific Ocean to the mighty Andes. It's a country full of larger-than-life landscapes. that seemed unconquerable in the late 1800s.
The Andes Mountains in Ecuador run north-south for about 600 kilometers with peaks over the 5,000 meters and then actually getting down to zero level. It was very important to connect the capital city, Quito, and Guayaquil, the main port, that were geographically separated.
Although only 268 kilometers apart as the Condor flies, these two strategically important cities were separated by raging rivers, dense cloud forests, and deep ravines. The ambition was to build a railway across this terrain. But as Tren Ecuador's Alex Ortiz knows, achieving it would be no mean feat.
Guayaquil, it's in the lowlands at sea level, and Quito, it's over 2,800 meters above sea level and then getting to the Central Valley. So the engineers had this incredible task to go from the coast through the mountains, through this steep valley. It's very difficult to imagine a train going through these mountains, through these vertical walls.
For centuries, the perilous journey between the two had only been possible by mule, taking up to 12 days to complete. At the end of the 19th century, the country's leadership enlisted the help of two American brothers, John and Archer Harmon, to start work on the Trans-Andean Railway. But there was one section that was seemingly impossible to overcome. The Devil's Nose. With its precipitous drops and impenetrably hard rock face, building a track that could circumvent and ascend this section would pose one almighty engineering challenge. But inspiration lay, incredibly, in their surroundings.
So the trails that they are all around over here, the ancient trails in zigzag, like a switchback, like the ones I have on my back. They thought this could be the great solution.
In 1908, after 10 arduous years of construction, using a workforce of thousands, the first major rail network of the Republic of Ecuador was completed, finally connecting Quito and Guayaquil by rail.
This is the Devil's Nose, a historical railway, a feat of engineering. I've seen it many times and it still blows my mind. It's incredible.
Made possible only by a feat of engineering at this most imposing section of the line. This is one of the highest active narrow gauge railways in the world. Tour guide Santiago makes this world-famous journey on a regular basis.
I never get bored of sharing this route with the world. It's pretty amazing. The landscapes, it's an amazing route.
The ingenious solution engineers turned to was a switchback, a zigzag section of track with reversing points. This enables the train to traverse this extreme gradient and gain 100 meters in altitude as it travels between two switchbacks.
So right now, we are going through the famous Devil's Nose. So we're going up through the track in reverse, 1 kilometer, gaining about 80 to 100 meters in altitude. What is important to mention about this maneuver that is pretty amazing is that the mechanism to allow us to exchange the tracks are hand-pulled by the brequeros, the members of the crew. Right now, the brequero leave the car, pull the switch, allowing us to go through it in reverse. Again, when we reach the end of the zigzag, there we will stop for a few seconds. The brequero will leave the unit again, pull the switch, and from there we go straight forward. You look closely to the window, you get lost in the view, and you feel like you're floating in the train through the track.
This inspired concept solved the most troublesome section of the railway. And in doing so, a journey that once took 12 days was reduced to just 14 hours.
The establishment of the track for Ecuador was something very important. The connection was better, transportation of goods, cargo, passengers, so there was a better dynamic on the communication between the two main cities, Guayaquil and Quito.
Despite flood damage in 1998, which destroyed much of the line, the Devil's Nose section never closed.
The engineering behind the Devil's Nose is outstanding. To get through these mountains was thought impossible for so long. Despite the massive challenge of building the Devil's Nose section, today, over a century of being built, is one of the most stable areas of this line. And that's the testament how great was the switchback solution. I think this is probably the most incredible railway in the world.
Finding a route that can reduce the gradient is one way to tackle a mountain. But some inclines are so extreme, their engineering is from the realms of science fiction. Some railway tracks are made for inclines. But people always want to get to the top faster. Come on! The obvious solution is building a line that's steeper still. But the steeper you go means your train might get there, but your passengers won't. Hey! With steep-sided mountains and Arctic winters, at 1,300 meters, the alpine village of Stows in Switzerland is about as remote as it gets. Popular with skiers, its tiny population of about 100 dramatically swells to over 2,000 during peak season. For the village and its visitors, an aging funicular was their only connection with the valley below. But this vital public service was failing to keep up with the needs of the passengers. Senior engineer Bruno Liefert was all too aware of the increasing demands it had to meet. It had to go faster, carry more people, and be easily accessible.
Here we stand on the old Stoßbahn. This, in 1933, it was really the steepest funicular in Europe. But the track is going around the mountain with 120 degrees. And we had to find out a new track possibility with a straight track. So therefore, after 84 years in use, we had to replace it and we had to build it in parallel to the old funicular.
But to find a new route meant confronting grueling mountainous terrain.
They told me, Bruno, you're crazy. That's impossible. But I was not happy with this answer, so I challenged them and say, hey, as long as you don't say it's a no-go, we will find a solution. And now you can see the solution is built.
Stoßbahn, the greatest incline ever conquered by rail, opened to the public in December 2017.
We have done something nobody else has done before, so it's really a new area and we created a new type of funicular.
Ascending a whopping 2,500 feet from the base of the mountain, at a jaw-dropping angle of 48 degrees. This 21st century funicular is truly groundbreaking. With such a precipitous incline, keeping the passengers upright on the journey was the first challenge. The answer was a cutting-edge carriage.
One of the main goals of the new Stoßbahn was we make it horizontal at both stations.
Mechanical engineer Niklaus Moser was part of the design team.
The demand for easy access for the passengers is increasing, and then we have some very steep sections and flat sections which really required a leveling system, and that was achieved with the new system.
What the team came up with was a carriage with a fixed chassis and individual cylindrical cars that rotate to keep the passengers and freight horizontal at such a steep angle. It was the first of its kind in the world. Having to fit essential testing and maintenance of the carriages around a busy timetable, Niklaus and his team make the most of the 15-minute window when the train is in the station.
We now are below the train where we see best how the leveling device is done during the ride. And then you see these two cylinders on the left-hand side and the right-hand side. They are connected to the lower part of the round-shaped cabins. And once they move this way or that way, that means that the cabins are rotating around.
Inbuilt inclinometers sense the angle of the track, signaling the hydraulic cylinder system to kick in and compensate for the incline. By rotating the carriages accordingly, always keeping the floor horizontal and the passengers upright.
You don't really feel that the train is changing the gradient as you stay on the floor. You just glide up to the top station and you don't feel it.
A routine test reveals just how the mechanism works to overcome the 110% incline.
So now we are testing again and we go to a full inclination of the train on the track would have. Respectively now here our cabins. I'm holding on strong here that I don't fall over. We're not yet there, but we're getting there. I hope my muscles are strong enough to hold on till we ever get to the very end. Oh. That's the limit. Jetzt müssen wir noch rauskommen.
High-altitude railways. Testing the limits of engineering to conquer nature's most difficult terrain. And one ambitious train that faced a series of problems is the Stoßbahn funicular. Today, project leader Bruno is heading back to the site of the Stoßbahn's most demanding engineering ordeal, building the track. Even now, the final stage of this journey is not for the faint-hearted.
The challenge here is because the natural wall is more or less vertical, so we have to find a way, and so therefore we created this tunnel with 48 degrees.
3 tunnels would be cut through solid mountain, starting with the highest, excavated using the simple drill and blast method. But with a near vertical gradient, the lower 2 tunnels would need a completely new approach.
So the steepest area is right here and the next 200 meters down. This tunnel here is 250 meters long and 200 meters of these 250 are 110%.
The team used the raised drill technique with a specially designed drilling device. A very small pilot hole is drilled using a directional drilling tool. Once it emerges, the drill is then replaced with a rotating metal cutting tool, which is drawn upwards, creating a wider circular hole big enough for the explosives to be inserted and the tunnels to be enlarged to their final size.
That seems to be the most efficient method to create tunnels in such steepness. During the enlargement, all the rocks which came out went down because it's so steep, and the total amount was around 25,000 tons of material which we had to move.
Having managed to use it to their advantage with waste disposal, gravity still posed a significant risk for the construction team harnessed to the mountainside.
One of the biggest challenge was really here to ensure the safety for the workers because it's so steep When you lose, for example, a tool, and somebody else stands 10 meters below, this tool will have such an energy that is very, very dangerous. I can say now, really to summarize, we didn't have any really strong accident, and therefore we are very thankful.
At 1,738 meters long, the new track includes 580 meters of some of the steepest train tunnels in the world.
Sunday you're out in the open again, and then the next tunnel is coming, getting same steepness, and it's really rather an amusement ride than a transport from A to B.
Two of these massive motors enable both carriages to achieve maximum speed, whatever the gradient.
Actually, we are now in the machine room, that's why it's a bit noisy. That's the bull wheel. It's actually transferring the movement from the motor to the rope, and the rope is connected then to the car. That's how the movement from the drive here, from the bull wheel, is transmitted to the car. Imagine 36 kilometers an hour at 50 degrees inclination. That's a big speed. It's the fastest in the world on an inclination like 110%.
Accomplishing all the demands it set out to achieve, the Stoßbahn can carry 1,500 people every hour on the steepest railway in the world.
Travel speed is about 2.5 times as much as the old funicular was. The cars are bigger. This means that we have drastically increased the transport capacity.
Every day, the brilliant engineers of this futuristic funicular keep the villagers and their visitors connected.
All the time when I see the train is passing here, it's a great feeling. It's in a way undescribable. After 14 years hard work, I'm so proud to see how the train goes up and the baby's really born and it works.
But for other railways around the world, a climb doesn't have to be steep to be an enormous engineering challenge. Birmingham, a city in the Midlands of Britain, and one that in the 18th century was striving to be at the heart of industry. But without a railway connecting the city to a major port, it was yet to become a reality. Civil engineer Fraser Godfrey is at a site on the outskirts of the city that would see engineering opinions divided.
Birmingham, by the late 16th century, was a centre of manufacturing. So growing in its industry, it was very keen to connect to Bristol in order to facilitate that transportation of goods, possibly around the world.
At that time, the port town of Liverpool had direct trade with America and was thriving. Bristol and Birmingham dreamt of a link that would allow them to compete with these big coastal cities and boost their economy.
In the 18th century, the only way to get from Birmingham to Bristol was via canal, and that was a 6-day journey. So really, railways became an obvious choice to use to distribute their goods around the country.
But there was one major obstacle for engineers to overcome.
Birmingham, as we can see quite clearly here, is on a plateau, and it is about 70 metres higher than the surrounding area.
Along the southwestern edge of the plateau are two parallel ranges of hills with a valley in between, known as the Lickey Hills.
Hills are a great engineering challenge. How do you overcome a hill?
Determined to conquer the incline, the rail company called upon some of the world's best engineers, including Isambard Kingdom Brunel.
His approach was to take a different route to enable a much shallower gradient, about 1 in 300.
But Brunel's proposed route would take the railway 5 kilometres further east, making it longer and more costly to build. Instead, beating him to the contract, Captain William Morsum came up with a much bolder solution.
He decided on this route straight up the side of the Lickey Hills, which formed the Lickey Incline.
A 3.2 kilometre stretch with a gradient of 10 degrees. around 10 times steeper than heavy trains of the time could negotiate. And the only way to overcome the gradient would be to use an additional engine, designed to push each train up the incline, by giving an extra boost of power, an ingenious system known as banking, and one that they still use today. Engine driver Richard Higgins is taking to the line to bank a freight train.
We're now departing to go to Bromsgrove via New Street. The train we're due to bank should already be here because we've been put down into the platform. We're just coming into the station now. We're going to go up beyond the train that's due to be banked. I think it weighs about 1,300 tonnes.
There are two methods of banking: buffering, which is simply pushing the train, or coupling, attaching the banking engine to the train it is assisting.
Some trains now use auto couplers for an automatic release. You press it, it releases the jaws, it lifts this up, which lifts the locking mechanism underneath, lets the jaws open, and the train will pull away from you, and you just fall back away from it. Hello, Bromsgrove, 0 Bravo 01. I'm buffered up behind 6 Zulu 46 now and ready to depart. With this train now, I just have to push it up the bank. If it's got the auto coupler on, you set the auto coupler up and you couple up to the train and you use this control here, the master switch, and that's your remote uncoupler. And now when you do that, the train in front will just pull away from you when it's reached the crown and it's starting to drop away. Right, we're going.
Today's more powerful locomotives are able to cope with the incline. But the principle of banking is still needed for trains heavier than 1,200 tonnes or those with a low coupling strength.
A lot of the freight trains that come up here, the majority of them do need banking. It's an important job for us because otherwise they'd have to be diverted and they go a long way round, which is not very economical fuel-wise.
It's the maximum horsepower of 3,300 that these mighty banking engines provide that make it possible to push 1,000-ton trains up the incline.
Right, we've just come off that. This is the top of the incline, a place called Blackwell. We've just come off the train now because he can carry on his own from here.
And this is still the main rail link between Birmingham and Bristol, made possible by the steepest sustained mainline railway incline in Great Britain.
So as a piece of civil engineering, the Lickey Incline is really quite basic. It's a railway up the side of a hill. But as a piece of mechanical engineering, this challenge forced engineers to develop more and more powerful locomotives, which helped with the development of locomotives, ultimately across the world.
Mountain railways, overcoming mighty peaks to connect some of the most remote destinations. But some railways are renowned the world over for their heritage. Going up one mountain is straightforward enough. But when you have to go through a whole range of them, there's a challenge around every corner, and every corner is a challenge.
Oh, come on!
The Alps, Europe's highest and widest mountain range. Covering 1,200 kilometers of forbidding peaks and valleys. This impenetrable landscape should put the brakes on any plan to build a railway. But in the heart of Austria's Alpine country,
Ja, wir fahren hinten auf dem ersten Plattform. Ja.
Operation Manager Klaus Bernesch is taking to the tracks to see how a seemingly impossible line through the mountains became a reality.
Riding on the locomotive is an experience because you feel the power of the steam being freed into the pistons, work there, and do propulsion to the train. It's almost a living animal.
Today, trains like this one carry tourists. But in the golden age of steam, they played a vital role in trade across the mighty Austro-Hungarian Empire. The steep peaks of Austria's Semmering Pass, though, made plotting a route for the trains to travel here an engineer's worst nightmare.
Looking back to the 19th century, the main part of Austria in the town of Trieste was blocked by mountains to Vienna. So a railway line had to build across the mountains of Semmering.
895 meters above sea level, the steep gradients and tight curves the line would need to navigate left many convinced it simply couldn't be done. But one man thought otherwise. In 1848, engineer Karl Ritter von Geiger decided he could defy the odds.
I think people thought Geiger was a little crazy, trying to operate a new railroad line. But today it's the same. How do some people think about NASA's ideas to travel to Mars?
His solution to overcoming the perilous pass was the game-changing Semmering Railway. The first mountain railway ever built. Its 41 kilometers of looping tracks carve a path through the landscape, with 15 tunnels and 15 viaducts.
The Semmering Railway is the first railway line in the world to become UNESCO World Heritage, and so is very famous all over the world.
Heritage rail expert Kirsten Ogris has come to Kalterinne, where the monumental scale of the task which faced Geiger is still clear to see today.
We see here the Kalterinne Viaduct, one of the most important viaducts of the Semmering Railway.
Standing 46 meters high and curving 189 meters across the valley. Its rows of towering arches are a testament to the treacherous terrain the line needed to cross.
A big challenge was these viaducts have narrow curves, and this in combination with the gradients, it's very difficult to build it. And they use such ordinary simple tools. They take the stone chisel and an ordinary hammer and also this iron to split the stones. It is very amazing when you think about that this big viaducts only made by hand.
But deep ravines weren't the only obstacle Geiger had to overcome. The route he chose meant trains had to climb a precipitous 457 meters height difference, an impossible feat for existing locomotives of the time.
Semmering features grades, curves, and mountainous terrain that has never conquered before by a railroad in Europe. At first, Geiger took a regular engine and made trials on a test track that had a steeping gradient, and he found out that a regular engine can operate over the gradient. It's because of the very low friction between steel wheels on steel rails.
Negotiating both gradient and tight curves called for a brand new, bespoke loco and some inspired thinking from Geiger.
He started the Semmering competition, where several manufacturers of engines could provide their ideas how to conquer the steep grades. The contestants managed to cover the already finished section of the line, but no model was suitable for a long-time operation at reasonable costs.
Instead, it was one of the contest judges, engineer Wilhelm Freiherr von Engert, who solved the conundrum.
After the competition was held, Engert found out that there are several good ideas that could be useful, and he implemented those ideas into his design, altered it a little, and a useful engine was the result.
Although built around 60 years after Engert's engine, this MH-class locomotive shares the innovations which made it so groundbreaking.
When you approach the engine from the front, you find a regular gearbox, the cylinders underneath, the smokestack. It becomes very special when we reach the point where the engine connects to the tender. Normally, a tender is a regular coach filled with water and fuel.
Unlike traditional trains where the tender is a separate wagon, Engert's idea was to build an engine and a tender on an articulated frame.
You see here the end of the locomotive and the beginning of the tender floor. And putting the tender frame outside, up to this point, you provide a bigger space for a larger firebox and thus the capability of producing enough steam to go uphill for a long time.
The extra weight of part of the engine on the driving wheels of the tender helped increase the traction on the rails. Engert's solution also helped solve the problem of navigating the snaking sections of curved track.
Imagine going through this tight curve with a locomotive that is very long and has a rigid axle base. Like a straight line, if you draw the straight line, once you will reach the other rail and you will be squeezed between the rails and not able to move forward or backward. Engert solved this by putting a pivot point in the middle of the locomotive, so it's bendy. As an example, you have the pivot point and the floor of the engine, the floor of the tender, as seen from above, and the tender can move freely towards the side using the pivot point.
In 1853, Engert's locomotive successfully traversed the entire 41-kilometre length of the Semmering line, finally connecting Vienna with the sea and completing Karl Ritter von Geger's railway through the Alps.
Geger was very intelligent and a great visionary. And of course he had the courage to do this, to realize this project. So he was perhaps crazy.
Since the invention of the railway, mountains have been their major adversary. Inspiring remarkable creations.
It was the highest mountain they pass by railway, so it was a big challenge for the engineer and also for the human.
Elevating engineering to new heights.
It's absolute genius with marvelous machines and engineering of the whole mountain rail system.
To create impossible railways.
It's really a great experience to see it running. I think it's an amazing engineering achievement, pretty special.
Despite being able to weave their way across the planet, covering colossal distances on cross-continental journeys, trains are in a league of their own when serving the world's cities. Many of our busiest metropolises thrive on the existence of the railway, transporting the population on its daily commute, getting goods to market, and visitors to great landmarks. But the urban environment poses some remarkable challenges for railway engineers. From troublesome inclines,
you can see the challenges that are faced, and as you can see the undulating territory and how steep these hills are,
to keeping up with the movement of freight.
Our biggest challenge is the new generation of vessels. And it's one challenge to work the vessel, other challenge to get them into the hinterland.
And delivering vital services.
The post office was going to have to find a faster and more efficient way to get that mail around town if the capital was going to stay connected.
And it's one such seemingly impossible challenge that has been facing engineers in New York for decades. As a city grows, so do the demands of its railways. More people means more trains to move them. But what happens when a city grows so fast, the railway just can't keep up? New York City, a metropolis that relies heavily on its railways. With around 90 million passengers a year travelling to Manhattan from Long Island to its east, the busiest commuter line in the US is desperately overstretched. To relieve the strain, engineers and construction workers are at work in the very epicentre of the city's railway network. Not that many would notice.
So we're here in the heart of Grand Central Terminal. This is where hundreds of thousands of passengers a day come through to take the trains.
Mike Pujak is part of the team working in near secret to solve New York's commuter problems.
Given how packed and congested Midtown Manhattan is, we have to work like a stealth project. All of our materials and all of our equipment still, to this day, has to come in from Queens and the Bronx to feed this job.
Despite the challenges, the city's non-stop transit system is operating undisturbed.
It's remarkable that hundreds of thousands of tourists and commuters come into Grand Central every day, into this iconic structure, and don't have any idea of the magnitude of the construction that's going on right below their feet.
The East Side Access Project. With ambitions to completely transform the transit network in New York, it's an undertaking on a truly grand scale.
This is one of the largest infrastructure projects ongoing in the U.S. right now. This is incredibly important for New York. This project is $11.1 billion, and we have right now currently about 1,600 people working on it. And at one point, we peaked out at 2,600 people a day working on this project.
Connecting one of the world's largest railway commuter stations with the busiest commuter railroad in the US via more than 12 kilometers of tunnel, East Side Access will carry trains along a network of new and refurbished tunnels into a 4-platform, 8-track terminal directly under Grand Central Terminal and Park Avenue. It's a giant space that must be constructed from scratch. And that's easier said than done when you're operating under some of the most expensive real estate on the planet.
So we're in the East Side Access Caverns here, and we're 150 feet below Park Avenue and Grand Central Terminal. If you don't carefully plan what you had to do down here, you will wind up creating a situation where you could disturb the ground because it could influence some of the structures above.
With the consequences of any errors adding to a potentially multi-billion-dollar disruption, it's a scenario that had to be avoided at all costs.
We could not interrupt this economic area and the traveling public coming into Grand Central, because that's a lifeline for the economy in this area.
To create this vast underground terminal, Mike and his team utilized an appropriately awe-inspiring solution.
Just to set the stage here, this is all Manhattan bedrock. There was nothing here. And then we used drill blast methods to basically carve out the balance of the structure. It's controlled blasting. And so you basically calculate the amount of powder you're going to use to control how much rock you want to remove, and then you measure the vibrations so that way you don't impose any issues to the buildings and the structures above. When finally excavated, this space was 1,150 feet long, which is larger than the Chrysler building is tall, and it was 60 foot high by 60 foot wide, and we have 2 caverns. I mean, to do 2,500 blasts under Grand Central and not impact them required a lot of coordination with Metro North.
Work on this supersized city railway began in 2007 with the launch of a pair of giant tunnel boring machines under Manhattan. Using powerful cutting heads to burrow through the layers of dense rock, the tunnel boring machines were set on course towards Grand Central. As tunnel engineer Jeff Rice recalls, operating in the heart of New York caused complications.
We were in a burgeoning city somewhere where there wasn't already an overfilled Penn Station and a historic Grand Central in the way, completely developed Manhattan, heavily traveled train traffic areas, and within the project limits, the project would have been much simpler.
The huge volumes of rock and muck generated by the tunneling process meant removing it created a logistical dilemma.
Since we couldn't bring muck up through Grand Central, and it was not viable to bring it up by train out of Grand Central, we needed to bring it out where it could be handled for trucking.
With working out of the overcrowded centre of Manhattan not an option, the team had no alternative but to take the muck the long way round.
The rock removed from the tunnels was then brought back entirely through the second tube of the existing tunnel on a conveyor system out to Queens. The sheer volume of rock that was removed for the length of all the tunnels, it's time-consuming.
Stretching for almost 2,000 metres, the giant conveyor fed out to a construction yard where rubble was loaded onto trucks.
Thousands of tons of material was brought out. The tunnel has become pretty much a highway for all the resources in and out of the tunnel.
But one section of tunnel under Queens poses East Side Access's engineers with a particularly tricky set of problems.
There you go.
With soft ground, a high water table, and a mass of active city infrastructure to contend with, inspired engineering solutions are required.
What we're approaching is one of the greatest challenges on the East Side Access project, is the Northern Boulevard crossing. As you can see, Northern Boulevard at midday is still a heavily traveled truck route. There comes a Astoria line train on the elevated structure. On top of the elevated structure and Northern Boulevard, underneath Northern Boulevard is a 5-track subway structure, one of the heaviest traveled lines in all of New York City.
To get the trains for East Side Access to their destination, the route must cross directly below these 3 major transport links. But the challenging ground conditions leave only a small area of viable material to tunnel through, and little margin for error.
All the traditional methods, and particularly methods that were tried and true here in New York City and in North America in general, they met defeat. We didn't want to do something innovative, we had to do something innovative here.
With just 3 meters of soil between the subway and the new tunnel, the engineering required to solve this problem had to be bold.
This is one of, if it's not necessarily the first, but this was the first time for a tunnel in North America where we were able to horizontally freeze the ground. Freeze pipes basically carried tubes that ran back and forth to a freeze plant. The freeze plant used a chilled brine to pump the chilled brine through all of the pipes individually and freeze the ground slowly.
Creating this frozen layer of earth helped to strengthen the ground sufficiently to tunnel in safety.
The frozen arch performed better than we expected. That provided the initial support to allow us to actually perform our sequential tunneling underneath. to protect the subway box and the elevated structure and the street. It very high stakes, but in the end, it was a very big success, and I'm very proud of it.
Work to complete this railway is ongoing, but East Side Access will also need to be able to handle the demands of a mass of New York commuters.
In a peak time frame when this job is running, Long Island Railroad plans to move 24 trains an hour into the terminal. And that's adding a lot more people down below, 150 feet below Park Avenue, that have to get out to the street. And with that, that'll be 160,000 people that have to be moved. And we needed to figure out a way to do that.
The answer, as with all things on this impressive urban project, is on an enormous scale.
We have 17 high-rise escalators all together that will head down to the caverns below. They're 90-foot high escalators, and when they're completed, they'll be the longest escalators in New York City, and some of the longest in the country. At a 150-foot run, these are some massive escalators that are being constructed here to connect the concourse with the caverns down below. Right now, we're rigging in one of the truss sections, so the escalator comes and putting it on the incline, and then they'll bolt it up together, and then they'll install the next one. You're working on 30-degree slope, so everything's cabled back and winched back, and they use a whole bunch of chain faults to lower these things safely into place so they can interlock them and go to the next unit.
Huge volumes of passengers are expected to flow into the new terminal each day, so the efficient movement of people will be essential to the project's success.
We're heavily relying on passenger flow, utilizing these banks of escalators. These are what will be the main feed of bringing everybody up from the caverns or down to the caverns, up to the concourse level, to the street, and into Grand Central proper itself.
But simply getting these giant escalators below ground has been a challenge in itself.
The contractor has no access from Manhattan to build out this job, which is kind of unique. We couldn't come into the middle of 42nd Street and Midtown and just start taking out, and doing an open cut. We had to bring in everything from a remote area, from Bronx, on work trains, just to access this.
It's another epic achievement in a project that, once complete, will stand amongst the most impressive feats of urban railway infrastructure anywhere on the planet.
Everything on this job is larger than life. The tunnels are more difficult than the usual tunnel. The soil conditions have been more difficult.
And despite all the obstacles, the goal is to unveil East Side Access to the commuters of New York in 2022.
When this is done, we're going to greatly improve the access to New York City for riders from Long Island. It is a significant achievement, and I'm proud to have this on my resume.
Thanks to the hard work of Jeff, Mike, and many more like them, the city will soon be able to rely on another impossible railway.
It was personally rewarding to work on a project this long and know that it's going to be around for generations to come and really change the infrastructure in Manhattan. For what was once just bedrock, turning into this grand, historic landmark structure that it will be. It's an amazing project.
Urban railways, built to overcome the demands of our increasingly populated cities. Evolving with these ever-expanding environments. Thanks to the planet's most pioneering engineers. Trains have to contend with all manner of obstacles in cities.
Hey, come on!
But when it comes to getting people from A to B, inclines can feel like a challenge too far. Both man and beast can struggle with slopes. As for trains, they can simply run out of steam. On America's West Coast, one city in California presented railway engineers with a similar set of problems. San Francisco, famous for its notoriously hilly geography. It's a daily challenge that local Ed Cobean knows all too well.
Well, as you can see, walking up these hills suck. It's so steep, and living in San Francisco, there's no way to get around it. You can see the need to be able to travel up and down these hills without having to walk.
Historically, horse and cart were used to climb the streets. But accidents were commonplace and often fatal.
Just imagine these streets being cobblestone, and with the fog or the dew or the mist or the rain, when you get a wet cobblestone and how steep these hills are, how would those horses be able to get up pulling a streetcar with people?
Clearly, an alternative mode of transport that could confidently tackle the city's terrain was needed. And the solution has since become one of the most iconic urban railways on the planet. The San Francisco Cable Car. Standing alongside the Golden Gate Bridge as a symbol for the city, cable cars have been running up and down some of California's steepest streets since 1873. And in the 100+ years since its opening, this remarkable railway has been declared a National Historic Landmark in the United States.
The cable car is a perfect fit for San Francisco.
It's an achievement that's thanks to the work of inventor Andrew Halliday. And keeping his seemingly impossible railway moving depends on an impressive engineering operation.
Right now, we're in the cable car powerhouse. This is the beating heart. This is what operates the entire cable car system that allows all the cars to move out on the street. The cables range anywhere from 2 to 4 miles, and they're all driven by these electric motors that are 750 horsepower each. And it's all being held with this cable.
Running at a constant speed of 15.3 kilometers per hour, these huge cables travel out under the city streets in a giant continual loop.
Once the cables leave the barn, there's a series of thousands of pulleys underneath the street. And the cable will ride on those pulleys underneath the slot of the rail.
Remarkably, it's a system that works in the same way today as it did more than a century ago.
Since the day it's been open, we're still utilizing the same processes and techniques that have been handed down for generation to generation to the entire staff who's doing today what somebody did over 140 years ago. It's the beautiful cars that people see that make up cable car in San Francisco, that make up part of the city. But it's here with the grease and the grime and the dirty and the loud machinery that is actually what operates and runs the cable car system.
But those beautiful cars are about more than just appearance. And the only way to appreciate what it takes to overcome the hills is to take a ride.
Slide all the way down for me, folks. Slide all the way down for me.
Ed's joining his fellow San Franciscans as they climb one of the city's steepest streets.
The only way to move and or stop the car is by the actions of the gripman. He's got all the manual levers from a track brake to a wheel brake to his actual grip that grabs onto the cable, and that's what makes the car propel.
The grip works in much the same way as a vice. When the lever is pulled back, a set of metal jaws or dies close around the cable, gripping it tight. And when the lever is pushed forwards, the cable is released. It's the secret behind how the cars can ascend San Francisco's hilly terrain.
So right now we're approaching Lombard Street on the famous Hyde Hill. This is the hill that's 21% grade. This is the steepest route that we have in the entire cable car system. So right now what the grip operator is doing is he's pulling back on the grip and the dies are clamping onto the cable, and that's what's propelling us up the hill.
But what goes up must also come down.
Hold on, everybody, going down a little baby hill. Nothing major.
And things get even more complicated when a car approaches a crossing.
So what's about to happen is we're going to cross over Mason Street. So what he's doing here is letting go so he can coast over the intersection so we don't run into the other cable underground.
Let go too late and the grip man could hit the cable at the junction and cause an accident.
So now we're coasting over the intersection.
But let go too soon and there won't be enough speed to clear the crossing.
So now we've regripped the cable and we're back on our way.
This skillful method is essential for the cable cars to operate around the city. But the toll it takes on the grip system means maintenance engineer Luis Corazzo is kept busy in the workshop.
This is like the engine, the propulsion system for the cable car. Without this thing, you're not going anywhere. So as you can see, these dies are completely worn out. I got to knock them out of the hinges to put these new ones back in. You're grabbing and releasing the cable. The cable just rubbing in it all day long and just tearing up the metal.
And without these regular repairs, the grip could cause serious damage to the system's other key component.
Got a cable car 6 tons weight. And you remember, it's carrying 6 tons plus the passengers in there. Pretty heavy. Right now, what I'm going to do, I'm going to completely disassemble it.
For Luis, this is nearly non-stop work, with a set of dies needing changing every 3 or 4 days.
We got brand new dies right here. They're ready to go back on into the grip.
But without it, the cable cars simply couldn't function.
So this work definitely vital. I can take it apart, put it together in the morning, and by the afternoon it could be worn out. And it is just a part of the cable car daily runnings. We have to get it done.
Thanks to the work of Luis and many more like him. Day after day, this iconic city railway keeps running up and down the streets of San Francisco, defying all the odds.
I mean, if you look behind us and you can see the hills and the grades that we have to deal with and how steep everything is, the cable cars were designed to be able to get through that treacherous terrain.
And there's little doubt that the cable car system is one of the most incredible pieces of urban railway engineering ever constructed.
It still stands the test of time today. 140 years later, we're still operating on the hills. There's no way I could ever understand or fathom what the city would be like without it.
Cities, an urban battleground for engineers challenged with building some of the world's most impossible railways. Where increasing populations and the pressure to bring people to and from the heart of these metropolises quickly demands serious innovation. For one city, it's an age-old problem. The railway is a great way to keep the lines of communication between people flowing. But when a city expands and its population swells, if the mail can't get through, then conversations could end up feeling a little one-sided. London at the turn of the 20th century. In just 100 years, England's capital experienced a rapid rise in its population, growing from less than 1 million to over 6.5 million. Under the strain of this hasty expansion, in a scenario similar to today's most congested cities, getting around became a serious problem, as physicist Andrew Steele is experiencing for himself.
In the early 1900s, London was one of the largest and most populous urban areas in the world. And just like today, congestion was a real problem. You can easily imagine these vans being replaced by horse-drawn carriages, but the problem is pretty much the same. It's not about how many horsepower you've got if you're just stuck in traffic like this. Been in this cab about 20 minutes and I don't think we've gone a mile. This is why I cycle around town normally.
But it wasn't only commuters that were suffering the consequences of the backed-up traffic. London's postal service relied heavily on the roads. But with mail coaches barely managing a crawl, the deliveries were suffering severe delays.
In those days, one of the most important ways to communicate was by post. And with sorting offices spread across London, the post office was going to have to find a faster and more efficient way to get that mail around town if the capital was going to stay connected.
Today, Andrew is en route to discover how one pioneering railway helped keep the lines of communication flowing.
The solution the post office's engineers came up with lies down here, 20 metres below the city's crowded streets.
In 1927, one of the most unique railways the world had ever seen launched.
Check this out. This is what they came up with, the London Post Office Railway. What an amazing contraption.
The world's first driverless electric railway. These miniature trains rode an underground network of 35 kilometres of track at speeds of up to 48 kilometres per hour, serving 8 stations and sorting offices. For 3/4 of a century, it ran uninterrupted, carrying up to 4 million letters a day. And London hardly even knew this ingenious system existed.
This is so impressive. I've lived in London for years and I had no idea that all this was down here, let alone that it was still running in 2003, delivering letters right across London. This place is now just a tourist attraction, but back in 1927 when it was opened, it was a real engineering pioneer, allowing it to run for an astounding 22 hours a day, delivering millions of letters all across London.
But constructing this urban railway and its labyrinth of tunnels was no mean feat. Designed to run trains that are 61 centimetres in width, Mail Rail's tunnels are just 2.7 metres in diameter, much smaller than those servicing London's passenger underground network today.
Wow, what an amazing place to be. We're going deeper underground and it's really quite cramped down here. Imagine the workers excavating these tunnels. It must have been grueling work and also not a job for the claustrophobic.
Underground tunnelling in London was by no means a new concept in the early 1900s. But the early work on tunnels for the tube network had been an arduous and dangerous endeavour, thanks to the challenging conditions. The layer of soft clay beneath London meant water could seep in, potentially causing the tunnels to collapse.
The post office were building over 20 metres below the streets of London, and so they needed this tunnel excavation to be quick and efficient, but most importantly, safe for the workers doing the excavating.
The innovative solution to this problem came from one of tunnelling's great pioneers, James Greathead.
The solution the engineers used was called the Greathead Tunnel Shield. It worked a bit like this cookie cutter. So imagine I'm trying to build a tunnel going towards you in this material here. What we can do is place our tunnel shield in position, shove it forward with a series of hydraulic rams, and as this cutting edge dislodges material, workers inside can excavate it, safely protected by the shield. Then, as it moves forward a bit further, we can start constructing the lining of the tunnel behind the shield as it moves, making the whole process fast and efficient, and most importantly, safe for the workers who are protected inside here.
This groundbreaking technique not only made it possible to build this railway, it also enabled the London Underground to dig much deeper, heralding the transformation of London's transport network. It took 3 years to dig the tunnel system for the Post Office Railway. Construction was halted when World War I broke out. But in 1927, with the rails laid, this innovative electric railway finally started operating. However, London's postal system would encounter another problem, one that threatened to derail the whole project.
The route between the stations was essentially a giant loop, and as you can see, the corners could get pretty tight. Now, in the original design of the trains, the wheelbase, so the distance between the wheels, was about 2 meters. So let me show you what that means by getting out this tape measure. You can see with this straight tape measure laying on the curve, it's just not following the track at all. What that meant was that there was a lot of wear and tear on the wheels, on the track itself, and in the worst case scenario, trains could get derailed, get stuck, and that could stop the whole network entirely. Now, a derailed train is really bad news for those letters and parcels making it to their recipients on time. So what was needed was some kind of engineering solution to allow the trains to navigate around these difficult corners.
If the engineers were to keep their trains on track and deliveries regular, they would need to go back to the drawing board and redesign them from the wheels up.
This stuff's all just been down here pretty much untouched since 2003.
To see the solution engineers devised, Andrew has been given special access to where the Post Office Railways fleet have been stored for decades.
This is the new design, and so the first thing we can do is get out the tape measure again and just measure this distance here between the wheels. It's about 1.30 meters or 1.40 meters, so much shorter. And the other big innovation is that this is connected into what's called a bogie. And it's made up of this big wheel here, which is the drive wheel, which is directly connected to the electric motor, which is underneath this section here. And then we've got this smaller wheel here at the back, which is connected to carry the weight of that carriage. And that means that this long carriage here is able to be articulated to rotate around this point, which is known as the kingpin. And that meant that these trains are much more flexible when it comes to going around tight bends. Additionally, it meant you could have a much longer carriage in between these bogies. This new design came with a number of significant advantages. Firstly, there was less wear and tear on the wheels and the track. Secondly, there was less chance of derailments. And thirdly, these lovely long carriages meant that we could carry more post beneath the streets of London.
Solving this final engineering puzzle enabled the Post Office Railway to run successfully for 76 years, reducing travel time across the capital and, in the process, alleviating congestion on London's busy streets.
This is pretty cool.
In the 20th century, this was a game changer for the capital. A hidden hero working tirelessly below ground to keep London communicating and in touch with the rest of the world. Cities, bustling metropolises that rely on the railway in order to run efficiently. Their unique conditions test engineers and demand the most innovative solutions to seemingly impossible challenges in order to keep our urban environments functioning. But for some cities, it's not the passengers that pose problems. Cities rely on trains to keep them fully stocked. But when freight is coming in fast, and those bringing it from ship to shore can't keep up, those delays could end up bringing everyone and everything to a standstill. Hamburg in northern Germany. Despite being positioned 110 kilometers inland, incredibly, this leading city of international trade has grown and thrives from its busy port, Europe's third largest.
It's hardly any distance at all from the centre of the city of Hamburg, and yet there's this huge dock.
Connected to the North Sea by the Elbe River, Hamburg links Europe with the trade from East Asia and the Baltic region. But this port became so busy that its infrastructure began to struggle. In order to keep up with the sheer volume of freight coming in, engineers decided to create a rail network like never before.
The sheer scale of this place is just incredible. It's taken us 5 or 10 minutes just to drive from one end of this terminal to the other.
In 2002, they opened the Altenwede terminal, the largest container rail terminal in Europe.
Looking around this port, you can see the crucial importance of rails, not just for the trains that ultimately take a lot of the goods out of this place, but for all of the operations inside the port. Everything is running on rails. Everywhere around me there are these giant cranes constantly, everything's bustling, moving these containers off the ships onto the land and then replacing them with new containers from over there, keeping this whole port moving. The real secret to this place's enormous efficiency is these things. And we've got a rail, looking much more like a conventional railway. But the thing that's weird about this is we've just got one. And if we were to imagine this as a train track, it has a ridiculously wide gauge because the other rail is somewhere over the other side there. This is an RMG, or a rail-mounted gantry. And what this allows it to do is move this huge crane system up and down along this massive stack of containers and access any one of them.
Historically, both the port and city have grown in tandem, with a road and rail network to distribute the cargo. But in recent years, a combination of ships getting larger and a global increase in the use of containers has led to a massive rise in the levels of cargo at the port. For sales director Thomas Lucia, keeping the freight moving is critically important.
Hamburg is one of the busiest industrial areas we have in Europe. 1990 we had a number of about 2,000 containers which were loaded and discharged. Now we discharge up to 40,000 of those containers. So the pure size of the volume has tremendously changed, and this is something I wouldn't have dreamed of 1990.
And by 2030, the volume of containers that the port will handle is predicted to increase by a further 43%. But located in the heart of the city, the port has limited space for expansion, leaving no other option but to find a way to handle the freight more efficiently.
One challenge to work the vessel, but the other challenge, that is what you exactly see here, is the challenge to get them into the hinterland. A truck, it can carry 2 of those containers. A train carries 100. So we need to use the capacity which we have in German and European hinterland best, because we will not get new train tracks, new motorways. We have to use them better than before. And the answer for that, for us here in the north, is the railway. When we started with this facility, CTA, 16 years ago, this was the first fully automated terminal, and I tell you, in the first years, everybody was laughing about us. Now it's standard. All new terminals worldwide, in Europe and in Asia, is developed the same way than here, because you get the highest capacity out of it, and you are damn fast.
This high-tech terminal has the capacity to handle cargo from 4 ships simultaneously and distribute it onwards into Europe, either by train or lorry.
Railways have long been integral to the distribution of freight once it comes off ships. But what's surprising is that as soon as this ship hits the quayside, it's immediately confronted by rails.
Container handling is divided into 2 stages. The first is at the waterside and is the only part of the process that requires a human crane operator.
Just look at the size of these cranes. These things are called ship-to-shore cranes for the obvious reason that they move the containers off the ships and onto the shore, and they are gigantic. If that top beam gets tilted up to its maximum height, it can reach over 100 meters in the air. They're called dual trolley because the top trolley there brings the container off the ship down to this level here, where a second trolley moves it onto some automated vehicles over on the other side. They are incredibly efficient and move huge, huge numbers of containers.
The next stage of the process uses a second type of rail-mounted gantry, automated stacking cranes. Two remotely controlled cranes working at different heights along a stack of containers, taking them to and from automated vehicles.
Mounting these RMGs on rails is an incredible example of engineering efficiency. This whole thing is controlled by software. The software says which containers are going to be pulled out, which trucks are going to be here to receive them, and it makes sure that this enormous operation can run smoothly and efficiently.
The Port of Hamburg's bold use of technology has transformed the way the port and city operates, with billions of objects connected to a computerized system via intelligent sensors.
The degree of automation here is just astonishing. You've got these thousands of transponders sensing the location of every one of those vehicles, not a single human being. And those things, there are some that are electric, there are some that are diesel powered, and when they run out of batteries or run out of fuel, they can automatically drive themselves to the filling station or to a different station that swaps out their batteries and gets straight back on with their work.
This groundbreaking solution to handling cargo means that the port can now process over 7 million containers per year, setting new global standards. In 2017, 58,500 freight trains passed through Hamburg Railport, transporting vital goods to its city and beyond.
This port is just such an impressive operation, and the whole thing is running on rails. To bring the goods onto this train track below me and transport the cargo all around Europe. It's just incredibly efficient, all of it choreographed by software, and without rails, that just wouldn't be possible.
Since the invention of trains, the cities of the world have given engineers some of their toughest challenges. Inspiring, daring solutions.
Yeah, the cable cars is the backdrop to everything San Francisco. And the grades that the cable cars overcome, it's amazing to think that everybody can enjoy and get around the city.
And groundbreaking innovations.
Nearly everything you buy, from food to clothes to cars, is shipped in these giant containers on these enormous ships. And without rails, none of this would be possible.
To create impossible railways.
While not impacting the everyday operations of the New York City passengers, we have been building one of the largest civil projects in the history of North America.
Since the invention of the railways over 150 years ago, engineers have been pushing the boundaries in the quest to reach the world's most far-flung places. Inspired by progress and driven by the desire for adventure, trains are continuously breaking records, traveling further and higher than ever before. But for train engineers, there's one ambition that provides perhaps their biggest motivation. The need for speed. But making trains go faster poses a unique set of challenges.
The problem is every time you go twice as fast, air resistance becomes about 4 times more of a problem.
Spain has some very interesting terrains, so engineers were given a challenge to deliver a very high-speed network.
We need to make the network a safer place, and at speeds that don't delay other passengers or freight trains.
And it was one such impossible challenge that faced engineers in America in the 1950s. Trains often have the edge over other forms of transport.
All aboard!
They're easy to access, and they avoid traffic jams. But in the quest to go faster, hitting high speeds can mean compromising something pretty crucial, if you're a passenger. Few countries' histories have been more strongly shaped by its railways than the USA. But after playing a vital role in the growth and prosperity of the United States for a century, by the 1950s, it was the glamour of the rapidly advancing aerospace and automobile industries which had begun to capture the imaginations of Americans, looking to the future, not the past. Today, engineer Dan Dickrell is in Missouri, at the wheel of an icon of America's roads.
This is awesome.
To track down the train that was designed to bring the railways back into fashion, fast.
This is a 1947 Cadillac and an amazing example of American automobiles of the time. People were falling in love with this car and cars like it. Why would you want to be packed into a crowded train when you could be riding in a magnificent vehicle such as this?
Compared to cars like these, the train was increasingly seen as a slow and uncomfortable way to get around, leaving it in real danger of being left behind.
It was clear that the railway industry had to come up with something quick, otherwise they were done for.
The task of revolutionizing train travel fell to General Motors, and their answer was the Aero Train.
The old iron horse ain't what she used to be. She's lighter, she's faster, she's the Aero Train.
Billed as the train of the future, its bold design aimed to make traveling by rail faster and more comfortable, to entice passengers back on board.
So this is it. It's the Aero Train. It's an unbelievable train. This train was the big bet. This was the thing that was going to save the industry, revitalize it, make trains cool again, make you want to ride on it.
The Aero Train was conceived in the mid-1950s by General Motors' legendary designer, Chuck Jordan. The train was deliberately designed to tap into the public's enthusiasm for the elaborately futuristic styling being used by car manufacturers.
Looking at the similarities between the Aero Train and the Cadillac, it's obvious the influence. The nose, the streamlining, it looks almost identical.
Taking further inspiration from the roads, the train's passenger coaches were even modelled on the same design as buses of the time. But this train had more up its sleeve than just ultra-modern good looks.
One of the solutions was materials. It was going to be made of aluminum, which was revolutionary because most trains at the time were made of steel. This made it very, very light.
At around half the weight of a conventional train, the Aero Train was to be transformed into a speed machine.
It was to be among one of the fastest trains in America. It was about 100 miles per hour would have been the top speed. It looks fast. That beautiful nose, that sweeping windscreen. The 1,200 horsepower engine could get it up to speed very quickly.
That is Mrs. N.C. Desendorf, who formally christens the aluminum beauty in recognition of its unique and revolutionary character. For the Aero Train is the answer to a request by the railroads for new ideas and equipment. Things that would cut costs, increase speed, improve riding comfort.
But in reality, it was a huge failure.
Having set out to transform the future of America's railroads, the combination of innovations rolled out on the Aero Train turned out to be a triumph of style over substance.
The engineering doesn't hold up. This area right here, this beautiful curve actually acts like an air scoop. Air is forced in with nowhere to go, slowing the train down. So it's an example of where the designers wanted some really, really powerful visual statements. The engineering says, this beautiful shape actually makes this train go a lot slower.
But aerodynamics weren't the only issue. As soon as the first passengers stepped aboard, that revolutionary lightweight body led to some unfortunate consequences.
There was a big problem. The cars themselves were so light, that the wheels had a hard time staying on the rails at top speed, so the passengers inside would be bounced around like basketballs, making for a horrific ride.
A problem made worse by perhaps the most innovative feature of the Aerotrain's design, one which was hidden out of sight behind the sleek bodywork.
So instead of traditional coiled mechanical springs, the Aerotrain had a system of pneumatic air bladders. Actually, if you can look up here, you can see them. They're positioned around the corners of the carriage.
However, Aerotrain's most startling innovation is its patented air ride suspension, which is achieved with giant air compressors in which the pressure is controlled for the load being carried.
Initially hailed as revolutionary, in theory, passengers would be isolated from the effects of vibration and body roll, literally floating on a cushion of air.
The pneumatic system of the Aerotrain is set up with pneumatic bladders underneath, air bladders, similar to these right here. The idea being the bladders and a control box system could adapt to the conditions of the train, the weight, how many passengers were, giving a tunable ride.
In reality, its novel suspension system was another engineering advance with huge potential, left unrealized within the Aerotrain.
We've got a board on top of very similar bladders. Now, this board, as we can see, with a little bit of motion, creates quite a vibrational ride. The quality of the ride is going to be similar to the water in this cup. So what I'm going to do is I'm going to apply a little bit of force here. And what we can see is a little amount of force creates a lot of displacement, sloshing the water around, meaning that the passengers in this particular carriage are being shaken all over the place. A very unpleasant ride.
A design fault which could have been easily rectified by making the carriages heavier, but at the expense of speed.
Now what this does, by adding the weights, it effectively stiffens the springs in the suspension system, the air springs, by increasing the internal pressure, creating a tension in the bladder. With a stiffer suspension and the added weight, the same amount of force applied creates less shaking, less displacement. The result is a more comfortable ride for the passengers of the carriage.
The Aerotrain's place in the history of American transport is a reminder of just how hard it is to achieve railway engineering's holy grail of speed and comfort combined. But General Motors went on to inspire the trains of the future, where air suspension systems of today allow passengers to travel in comfort faster than ever before. And while this train never went into full production, it's anything but a forgotten relic of the past.
Well, there's no doubt that this train did do what it was supposed to do, but actually it did something much harder. It captured the imagination.
It captured the imagination so much that even miniature versions appeared in theme parks around the country. And this one in Oregon still runs today, meaning over 60 years later, the Aerotrain dream still lives on.
People all over still love this train. It's a remarkable train in terms of its appearance. And even though ultimately it wasn't successful, I'm glad they tried.
Trains, conquering great distances at high speeds. Engineers are being relentlessly tested to their limits in the need to make the planet's railways run ever faster. But when speed is at the top of the agenda, a train is only as good as its tracks. If you're going to be traveling fast, everything needs to be in perfect working order. The slightest bump, a tiny dip, or crooked curve can seem a whole lot worse when you're traveling flat out. Britain, a nation that relies on speed to keep its vast rail network flowing. Its trains complete around 4.7 million journeys a day. on an astonishing 35,000 kilometers of track. But keeping this huge infrastructure in tip-top condition, against the clock, day in, day out, is an enormous and vital challenge that must be met. The consequences otherwise can be devastating. Historically, the lines were inspected manually, creating delays and eating up an astonishing 1.3 million man-hours a year. A new solution to finding and fixing faults was desperately needed.
When I started in 2001, we needed to test track more efficiently and make the network a safer place, and at speeds that don't delay other passengers or freight trains.
But what could test the tens of thousands of miles of tracks without disrupting one of the world's busiest rail networks? The answer? The new measurement train. A 125-mile-per-hour speed machine, affectionately known as the Flying Banana. To anyone who may see this train fly by from the platform, only its distinctive colour would suggest anything unusual. But on board is some of the most innovative kit in the world.
The new measurement train can test the infrastructure all over the country at line speed, which means basically we can put the train inside other trains' paths. That means we're not delaying passengers or passenger trains, we're keeping up with passenger trains. Without the new measurement train, those trains cannot run on the track efficiently. We test the track, make sure the track is safe, that allows the trains to run. Right, let's get on the train.
Today, engineer Richard Wilkinson Ford is boarding this specially converted Intercity 125 as it begins another epic shift, testing a section of the track.
The new measurement train can do round about 1,000 miles a day. So we're pretty well a 22-hour-a-day operation.
Kitted out like a moving laboratory, testing is made possible by unique cutting-edge equipment, designed to recognise faults at a mind-blowing 125 miles per hour.
The 4 screens we have on the right-hand side here are our plain line pattern recognition system. We've got a very high-powered white light shining down at the track and 7 cameras. We're taking individual photos every 0.8 of a millimetre.
That's an incredible 10,000 photos snapped every second.
We knit those photos together into almost a film to identify where faults are on the track. You can pick up individual stones. You'll even see numbers written on the sleepers.
At super high speeds, the Flying Banana's cameras, lasers and mechanical measurements are able to recognise 3 critical track defects. Twist, when one rail is raised or dropped, causing the train to tilt. A dip in the rail surface, which causes wheels to bounce. And inconsistent gauge width, which left undetected could lead to a derailment. If a fault is picked up, the images which are sent back to base will be analysed by an inspector and any repair work scheduled in.
Right, guys, whereabouts are we?
But in the most serious cases, a defect could be deemed as one needing immediate attention.
You will have a block the line fault, which is quite a severe fault. The system will give us an alert. We'll stop the train, get down and actually talk to the signaller. We're blocking the track, so no other trains can run, and we're basically telling the guys to get out there and get it repaired now because it's a dangerous defect.
To avoid these potentially devastating faults going unseen, depot maintenance engineer Roger Gaines must ensure the Flying Banana's innovative equipment is in perfect condition.
If you look, you can see there's a camera here that points in this direction, and then you've got one that points directly above it, and then another one that points on the other side of the rail, and the same on the other side. And then you've got one camera in the middle, and the system joins all those together to make one big long picture of the actual rail. It also works together with another system, a laser system, which is behind us, and that takes 3D images of the rail All those images are stored on computers above us on this train, and it looks at all the faults and can tell which ones are proper faults and how dangerous it could be.
As it speeds around the nation, the game-changing flying banana is transforming rail safety, with track breakages reduced from approximately 1,000 a year to just 100. And thankfully, today's shift detects nothing out of the ordinary.
Without this fleet of trains, the whole railway would probably grind to a halt. This fleet is crucial to making the railway more efficient and safer. This train is completely unique and a one-off in the world.
Maintaining tracks is vital, but repair works can only go so far when it comes to keeping the world's railways running. France, a nation with the second largest rail network in Europe. 15,000 trains speed through the country, carrying 5 million passengers every day. To keep up with demand, this heavily used network is in the midst of a huge program to renew much of its 30,000 kilometers of track. But this critical job is one that has to be done fast. Taking place at night, during a very small window when traffic flow is at a minimum.
That's what I say, you don't hear them coming. When you're next to a track renewal machine, even less.
Tonight, as the last trains pass through, engineer Carl Signier is part of a team near Maurienne, just south of Lyon, preparing to put in another intense track renewal shift.
You see here the grey sleeper, new, concrete sleeper, and the next one, this is the old one. That's the first sleeper to being replaced tonight. And here you see the new rail that's going to be put in there. It's like the roads, they have to be maintained. Otherwise, you will see green coming out and trees growing in the track, and that's a pity.
But the team are expected to replace almost 1 kilometre of track in the next 7 hours, a seemingly impossible task for manpower alone.
1 kilometer is about 1,670 sleepers that you have to place, transport to the site, and then the old sleepers back. That's more than 500 tons that you bring in, and then you have to bring out again. The rail as well, 120 tons of steel. It's just enormous, the stuff that you handle here.
It's a painstaking operation that starts with preparation of the line, cutting the existing steel track for removal.
This preparation work is very important. It's physics work, but it's just at the beginning.
It would take a team of 500 to replace such a huge length of track by hand. So the solution to making this colossal task possible is to bring in the real workhorse of the workforce. The P95 track renewal machine. A 220-ton train that can replace up to 1 kilometre of track in a single night shift.
The track replacement composition train has just arrived, and people now get onto the machine to unlock all the working tools. It's like a pit stop in Formula One. Everybody knows what he has to do, so they are successful.
This powerful 72-metre-long beast is engineered to work through the several stages of the track renewal process. First, the stripping. As the train moves, the old rail is pushed aside. Then the old sleepers are scooped out by a claw-like arm and moved by a gantry crane to the rear of the train. The ballast is levelled out. New concrete sleepers are collected and moved to the front of the train, where a conveyor belt delivers them into position. Finally, the new rail is moved precisely into place. As the train continues to move onto a new section, the team bolt everything together.
Such a machine is a very complex unit and it's lots of functions, but only a good crew makes it performing to its maximum.
So here you can see up here the old track with the old sleepers. So here they're removing some sleepers from the track. Every 60 centimeter, it's removing old sleepers from the track.
This mighty machine moves its way along, preparing the line for the new rail.
At this moment, we're putting the new rail on the sleepers. It's an operation that you have to carry out with concentration. Losing it, it can move and hurt somebody, so everybody is concentrated.
It is very important to get this section done. If you have a short time like tonight, if you lose half an hour at the beginning, every minute is a minute less on production.
Tonight's work is part of a bigger plan to upgrade half of France's entire network by 2024. So working at speed is critical. But with only half of the job done, there's a problem that even the P95 can't overcome.
The train is ready, but the overhead line has to be switched off. As long as this is not done, they cannot get the country cranes running. So we have no new sleepers here and we are blocked to wait that this is ready.
Without the power to the lines cut, the cranes on top of the machine can't move the new sleepers into place.
Sometimes it can take like 10 minutes, 2 minutes, but sometimes it can take hours. It's a big problem.
In just a few hours, the first trains of the day will be approaching.
It's quite intense today because we have some unexpected event. We know that a passenger are going to wait for his train at 6 o'clock in the morning. So we know the time is running. All these problems on the track could bring some delay of the train. And the baddest thing for the railway traffic is the delay. One train delay will make another train in delay and another train in delay.
It's a tense wait for tonight's crew. But finally the power is cut and the P95 has to make up some serious ground.
The country crane has brought in the first new sleepers and they come now into the section where we do the sleeper lading. Now you see the sleepers coming in. Up.
As tonight's window of opportunity closes, the P95 performs. An unsung hero of the railway network, reaching its seemingly impossible target once again.
Now the whole train is engaged, the last step. The old rail is being placed on the ballast shoulder. You have here tons and tons of steel, and at the end, you see a new track behind the train. It's very satisfying, yes.
Since the invention of the railways, engineers have been driven by one thing: the need for speed. From streamlined designs to sheer power. The world's innovators have tried everything in the quest to make trains go faster. The question is, what next? There's no denying that going fast can be fun. The wind blowing in your face, the thrill of acceleration. But push things to their limits, and those forces start to fight back.
Oh.
The need for speed has long been an obsession for the planet's railway engineers. And it's pushed them to design some of the most incredible trains ever built. They've tried it all in their endeavours to travel ever faster. But there are two obstacles standing in the way of achieving this ultimate ambition: air resistance and friction.
The first problem is the friction between the train and the track, those steel wheels rubbing against the steel track, heating up and causing energy to be lost. The faster you go, the bigger these problems become. And air resistance is even worse. Every time you go twice as fast, air resistance becomes about 4 times more of a problem. In order to tackle the joint problems of friction and air resistance as we travel ever more quickly, engineers are going to have to come up with some ingenious solutions.
Deep in the Nevada desert, the latest in the line of experimental high-speed projects is hoping they have the answers. Virgin Hyperloop 1. Using magnetically levitated pods, propelled up to 1,000 kilometers per hour through a low-pressure tube, it's an entirely new breed of super-fast vehicle.
When you see some of the footage of these experimental tracks, some of the tiny little pods moving at incredible speed down these tubes, you can really see why their creators think this could be the transport of the future.
This ambitious concept has been in development since 2014. Making it all possible is a team of engineers based in Los Angeles, including Kristen Hammer.
Hyperloop 1 is building a new form of transportation. We're going 2 to 3 times as fast as high-speed rail.
And the ingenious system dramatically reduces the forces that slow traditional transport down. By using magnets mounted to the pod that repel against the metal track to create lift, the carriages ride on a cushion of air.
It uses magnetic levitation, or maglev, to float slightly above the surface of the track, eliminating all of that contact force.
We don't have friction from wheels, so it allows us to go really fast, upwards of 1,000 kilometers an hour. There's no bumps in your ride, there's no turbulence. It's none of the discomfort that you associate with the uncomfortable parts of other travel.
But without an engine that drives the wheels along a track, an alternative method of propulsion is required. Incredibly, they're using groundbreaking technology pioneered as early as the 1950s by Professor Eric Laithwaite.
When switched on, this machine will levitate itself above this aluminium sheet and also propel itself along. Switch on. Perhaps that's a bit way out at present, maybe the year 2000. But what is concerning us seriously at this time is the possibility of using the same idea, but for guidance along a track. This is a scale model of a high-speed transport system. We don't yet know how good this system would be if it were scaled up to full size.
Andrew has travelled to a modern facility located in England's Midlands, where they're helping to make Laithwaite's dreams a reality.
This is a linear induction motor test track. It's essentially a scaled-down version of what they're proposing to put in the Hyperloop. And it's effectively a rolled-out version of one of these, a rotary induction motor, the sort that you might find in an electric car or driving your washing machine at home. This motor is made up of 2 main components, the stator, which is this bit around the outside, and the rotor, this bit in the middle that spins round, hence the name. The stator is made up of a load of overlapping coils of copper wire. And when you pass a current through those coils, it induces a magnetic field, which actually rotates around inside the motor. Now that rotating magnetic field induces an electric current, again, inside the rotor, which is made up of metal plates. And that means that the rotor is effectively constantly being attracted and repelled. That causes the motor to spin around. Now, if you want to create a linear motor, rather than rotating the rotor, instead accelerates it along in a straight line, what you need to do is get this stator and roll it out into a straight line. And that's exactly what we've got over here. You can see we've just got these huge loads of copper coils, loads and loads of copper wire wrapped around and around to generate a magnetic field. And then here we have effectively our model Hyperloop. Now, this one doesn't maglev, it just goes along on these wheels here. And then in the middle, we've got a big aluminium plate, and that's literally all it is, a piece of metal. And when those magnets are turned on, then they generate the magnetic field in the metal, and that magnetic field is what fires that metal down to the other end of the track. So let's give this thing a go. Wow, did you see the speed of that thing? So you can just imagine if you had kilometres and kilometres of these linear motors, how fast you could go. This is just such a simple, elegant piece of technology, no moving parts, and such incredible acceleration. That was amazing.
Thanks to linear induction, it's possible to move extremely fast without any contact with a track. But to overcome wind resistance requires further innovation.
Huge problems are caused basically by the train tries to push its way through the atmosphere surrounding it. Now, if you're in an aircraft, you can try and reduce air resistance by climbing to a higher altitude where the air is thinner, and so the force of air resistance is less. But if you're a train, you're stuck at ground level. So how are you going to get around these problems?
The answer is contained within the Nevada test track, known as the dev loop.
The pod is propelled through a tube where most of the air is removed. So we're at enough of a vacuum to give us an aerodynamic advantage, but not so much of a vacuum that it's very difficult or expensive to maintain.
By using simple vacuum pumps to reduce the density of air inside the dev loop, the pod can move in the more favorable atmospheric conditions familiar to an aircraft.
What that does is reduces the air resistance. It reduces the amount of air that the individual carriages have to push out of the way. And that dramatically reduces the amount of force you need to accelerate it and maintain those high speeds.
And the potential benefits of this super fast travel are equally exciting.
A journey that would normally take you hours is taking you minutes, and you really don't need to plan your entire day around your travel because the time taken to travel is so much less than what we're used to right now.
It's an enticing vision, and one that is due to arrive as soon as the mid-2020s.
Where the first route goes is not necessarily 100% certain yet, but I plan to travel to wherever it is and get my ride in with everyone else.
Thanks to Kristen and the rest of her team, our future looks fast.
Right now is a really cool time because we have multiple solutions for a number of our engineering problems, and now it's piecing all of those together. I'm so excited.
Speed. The driving force behind some of the world's greatest railways. The need to make trains run faster than ever before poses engineers with unique challenges, requiring the most pioneering solutions. But one country leading the race is Spain. When it comes to connecting cities, speed is everything. The easiest way to achieve this is in a straight line. But when you've got mountains in your path, you can tunnel some of the way, but sooner or later, you're gonna have to swerve the problem. And that will slow you down.
No.
Spain. Famed for its historic and thriving cities. Iconic centers of commerce, all sharing one goal: a need to be connected to each other at speed. But standing in the way is a seemingly impossible geographical problem. Spain is one of Europe's most mountainous nations. This lofty landscape is well known to engineer John Veach.
Spain has some really interesting terrains. Engineers love these problems to solve. So engineers were given a challenge to obviously deliver a very high-speed network. Some of these routes went through mountainous areas. That brought some challenges in the train technology, the infrastructure technology.
The only way to conquer this terrain is to twist and turn around the obstacles that stand in the way. But such frequent and tight cornering is the enemy of speed.
So Spain, with its geographically spread areas, cities, regions, and the real drive to really drive economy, bring people closer together, needed a solution.
Madrid to Seville has historically been a key route. But with the Sierra Morena Mountains in its path, a dated single track restricted train speeds to just 100 kilometers per hour. In the 1990s, a new twin track shaved 100 kilometers off the journey, but it still had no choice but to follow a similarly twisty mountainous route. The engineers needed a super-fast train capable of taking these corners on. The solution is the Talgo 350.
It's so different to anything else I've ever experienced in over 30 years' experience across the world.
This extraordinary-looking locomotive has helped to revolutionize train travel across Spain. Triumphing over the demanding landscapes, slashing journey times, and connecting distant cities.
So here I am with one of the Talgo very high-speed train sets. Been operating since 1994, 8 megawatts, operating up to 330 kilometers per hour.
It's an engineering marvel that's packed with high-speed innovations.
So a Talgo train has a very distinctive nose end, sometimes referred to as a duck piece, but indeed it's all about the aerodynamics and reducing noise through structures, tunnels, to achieve those very high-speed things. Reducing noise is a key element of a Talgo train.
The only way to really understand this train's high-speed success is by taking a ride. And that's exactly what John's doing today.
Okay, so we're now departed Madrid and we're moving gently towards operational speed, which will be around 300 kilometers per hour.
To navigate the twisting route down through the mountains to Seville while still maintaining such speeds, the Talgo has an ingenious approach to tackling corners.
We have a lower centre of gravity, so obviously the coaches are suspended in a very simple way, in a vertical situation. And then the weight actually balances lower, so enables the coach to swing. This pendulum system with a lower centre of gravity, which enables the coaches to actually naturally tilt through curves to enable higher speeds.
The passive tilting system, which acts like a pendulum, relies on a pair of air suspension cylinders and 2 straight bars that are mounted vertically at one end of each carriage. When the train enters a corner, the lower centre of gravity allows the coach to move outwards, allowing the faster speeds of the train. As the lateral forces from cornering acts on the train, one spring is compressed while the other expands, creating a pendulum-like swinging motion that allows the train to tilt into the curve and maintain higher speed. The faster the train runs, the more it will tilt, and the more the lateral forces are compensated.
So as the speed of the train increases around the curve, the vehicle body will actually swing out lower, which enables this faster speed of a Talgo train.
And the trains also have another cornering trick up their sleeve. Most ordinary trains have a fixed axle between the wheels. But this creates a problem when trying to go fast around curves, as the exterior rail is longer than the interior rail, which means the outer wheel needs to go faster. To get around this, the Talgo does away with the axle, as Deputy Manufacturing Director Jose Palomo explains.
We are assembling right now the running assembly. We have independent wheels. You can see here that this is independent. We have monoaxle in the rolling assemblies, Talgo technology. You can see here. It permits us that in a curve, the interior wheels going a little bit slower than in the other exterior wheel.
By having independent monoaxles, the wheels can travel around curves at the speeds they need, not resisting against the track. Travelling through Spain, these engineering innovations are enjoyed by more than just its passengers.
Our Spanish train drivers love to drive a Talgo train. With the lightweightness, there's the ability to achieve greater acceleration and recover time, if there is any instance, of course. But the fact that they say they prefer to drive a Talgo train, for me, is quite thrilling.
With Talgo's innovations, the journey between Madrid and Seville has been cut from more than 7 hours to 2 hours and 20 minutes. And passenger numbers have swelled from around 400,000 to nearly 3 million each year.
The two founding members of Talgo thought, actually, how can we go faster around curves, but actually maintaining the safety, the integrity, and indeed the lightweightness, which was always against traditional railway technology, which is heavier, more powerful things to make things go faster and more structurally safe. But no, they overcame that challenge and revolutionised high-speed travel.
And that revolution is set to continue. By 2020, Spain plans to have 10,000 kilometres of high-speed line, making its network the largest in Europe. It's a real testament to the positive impact that the Talgo has made.
Having worked and lived across the world and travelled and worked with many types of trains, for me, these are the epitome of success, and I am thrilled to be part of this.
Driven by the need for speed, railway engineers have pushed boundaries like never before. Creating thrilling train journeys.
Oh, I absolutely love it. Live and breathe it. This is just making such a positive change. And just this technology for me is a real proud moment.
Breaking records across the globe with incredible innovations.
It amazes me that we keep this fleet of trains constantly out there, making the railway a safer place.
And they continue in their drive to build impossible railways.
Look at it. It's such a special train.